Looks like we're about to begin. So first up, we've got the interdisciplinary capstone team 26-4, Robotic Explorer for Hypothesized Surface. Gonna come on up here. As we begin, we can give a round of applause if you want to. Just so you're aware, I'll be holding up cards that will indicate how much time you have left, just to give an indication. I was a bit surprised with this gig, so I'll need to draw them up, but you will see them as they appear. All right, we are at time. You may begin.
Hello, everyone. Welcome. We are interdisciplinary team 26.4, the NASA Psyche mission. This is our disclaimer, meaning all of the work that we've created is our own. It is not directly endorsed by NASA or ASU. Here's an overview of what we will be going over today, and we will be starting with meet our team.
Hi everybody, I'm Nicholas Javadev, I'm a mechanical engineering major.
I'm Nithya Kulkarni, the other mechanical engineering major.
I'm Gina Philippos, the computer engineer.
And I'm Norelli Rivas Castillon, the electrical engineering major.
Here's our advisor who has been helping us this past academic year. Ali Akun previously worked at Microsoft and is a part of the Electrical and Computer Engineering Advisory Board. Here's our sponsor, the NASA Psyche mission, and our liaison, Cassie Bowman from Arizona State University. Now going into our specifications on our project.
Yeah, so the NASA Psyche mission is a journey to a metal-rich asteroid that is located in the main asteroid belt. The main purpose of this mission is to get a better understanding of planet formation and of our own Earth's core. Our team decided to design and build a robotic rover that would be able to traverse the hypothesized surface that is found in Psyche 16. Some hypothesized surfaces that are found can be flat metallic, loose debris, and numerous craters. Some of the core goals that we implemented on our project was basic movement with wheels, sensor and data processing using the communication between Arduino and Raspberry Pi 5, and path optimization. Now we will be talking about our design approach.
Yeah, so our goal was to make a 6-wheeled robotic explorer, and the way this works is it takes a LiDAR at the top, which sees the surroundings, feeds information into the Raspberry Pi 5, which then sends that signal to the Arduino, which then tells all the servos what to do and how to traverse. The goal is to make full autonomous navigation, so without the need of human interaction with it.
As we are an interdisciplinary team, we had to figure out a way to coordinate all of our different subsystems and subsections into one project, and so in our next section, we will be talking about exactly how we did that. So we will be talking about our design specifics.
Yeah, so this is a rocker bogie suspension system. This is the bogie. It's the pivot that connects the rear wheel and the middle wheel, and it connects to the rocker. It's called the rocker because the thing rocks back and forth. It's a passive suspension system designed to keep all 6 wheels have constant contact to the ground and have full, complete traction on the ground at all times. This is a differential bar on the top, as you can see here. It is designed to average the tilt from all the rockers so that it keeps the housing level at all times. And when one side of the wheels are higher than the other, it will keep the housing level, reduce the risk of rollover due to a lower center of gravity. Some design considerations were based on when we wanted to do legs versus wheels. Legs had a higher mechanical complexity and much more energy inefficient. However, they have a higher ability to traverse uneven terrain. Whereas wheels were less mechanically complex and low energy or high energy efficiency, and but unable to adapt to many uneven terrains as well as legs would.
Moving into our housing, the main goal of the housing was to create something suitable for repeated disassembly and reassembly. Some of the design considerations that went into that were choosing the material. We chose to go with acrylic for easy ability to laser cut. And the components had to be fixed. Some of the specifics are of the internal design features to help that. And then the last thing of our design considerations was to have a detachable lid for easy access to the components. Some of the internal design features, we use nylon standoffs into heat set inserts to prevent stripping the threads of those screws and also to be able to have a secure hold in the acrylic. The walls are held together with brackets, and the lid is held on pretty tightly with a magnetic closure.
So jumping into the overall power system and how our rover is powered. So here is an overall schematic of all of the components that are used in the power system. Additionally, also some computational system components that are in here. But we are going to be talking about how the power flows through all of these components. So our rover is basically battery powered by an 11.1 LiPo battery that flows into a main 20 amp fuse. Then it flows into a master on and off switch that is able to safely cut off power to the overall rover. Then that power will be split into two separate branches, the first branch being the first one on here on the top. As you can see, it has its own main fuse, and this is just for extra protection. This is the servo branch. Then that 11.1 volts will be stepped down to 6 volts by using a voltage regulator, and this will provide 6 volts to 10 servos. Down here is our logic branch, and as you can see, this also has a separate fuse, and this is just for extra protection as well. That 11.1 volts will be stepped down to 5 volts using the voltage regulator to provide a stable 5 volts to all of these different loads that are used on the computational system. Here is a physical representation of all the components that are connected in the power system inside the housing, as Natio was explaining. As you can see here, the RP LiDAR is the computational component that's on the outside that provides some data to the Raspberry Pi 5. Then the Raspberry Pi 5 communicates with the Arduino here via USB connection, and then the Arduino provides information to the PCA to send to the servos. And that is connected using the voltage regulator with the 6 volts and then ground in the middle for common grounding. Also connected to the power system is an IMU. This is a computational system component. An IMU basically just provides more information to the Raspberry Pi 5 of where it's currently positioned.
Now looking into the computational system. So just to preface, full integration was not completed due to time constraint, but the system we'll be talking about is on the Raspberry Pi that we have. So starting off, the two big main tools that we used were ROS2, specifically the Jazzy version, and the SLAM toolbox. So ROS2 is a robotic operating system too, and it was mainly used as messaging between nodes such as the Raspberry Pi and the Arduino. The other tool was SLAM, which stands for Simultaneous Localization and Mapping, and this was used to be able to map out the environment around the rover, as well as figure out where it is for our core goal of path optimization. Here we can see at a high level the computational system that is there. And so the two main sensors that we use are the LiDAR and the IMU for positional information. For LiDAR, there's ICP odometry, iterative closest point odometry, and basically using math to figure out where exactly the rover is moved with just the LiDAR information. And then the IMU information combined together into an EKF fusion, which is extended Kalman filter. And that basically combines it for more accurate information overall. That is then sent to the SLAM toolbox, which for that mapping, to be able to create the map and figure out where the rover is on that map that's created. The map is then handed over to our navigation system, Nav2, which basically takes care of that path optimization portion, so path planning and controlling the rover. So as we can see here, it's split into two servers, the planner server and the controller server. Planner takes care of, once again, planning, and then for the path optimization, and then the controlling takes care of sending information basically to the rover to know how to get to that point. Both of these combined then create velocity commands so the rover knows where to go. Here, ROS2 is used in a custom ROS node to be able to send convert the velocity commands into serial communication to send to the Arduino. Once the Arduino receives this command, it uses I2C communication to talk to the PCA 9685, our servo driver, which then uses pulse width modulation to control the 10 servos. So alternative methods considered, we were considering single versus dual processor, specifically the Arduino Mega 2560 Rev 3 and the Raspberry Pi 5. We realized the Arduino is good for real-time signal processing, and the Raspberry Pi, in contrast, is better for computational power. So we decided to go with a hybrid method and use both. Another alternative method considered, it was LiDAR versus computer vision versus hybrid. Many systems we see now, such as companies with Rivian, use many different sensors, and hybrid is really good, especially for more accurate information, because you want to have many points of data gathering. For our specific project, we have to consider time constraint as well as budget, so we ended up limiting to 2 sensors, the LiDAR and the IMU. Here we can see some proof of life with the power system combined with the computational system. Here you can see the servos moving. And soon it'll pan over to RViz2, which is a ROS visualization software. And it will show the different points in pink for the LiDAR, seeing where objects are. As you can see with the points in pink here. To the right is the map that was generated, which the white representing open space, black means that something is there, and gray representing unknown space. We'll now go into our overall testing and results.
For our main testing, we performed integrated testing with one testbed that tested 2 operating systems. This is a model of what our testbed looked like. It was made to simulate Psyche surface. So using some planks, rocks, and sheet metal to kind of simulate what the rover would actually see on the asteroid. The first of the 2 systems we tested was a remote control operating go command. And so given the go command, the rover would just go at the speed given. And the second was autonomous navigation. In this one, it would trace the path, identify it, and it would choose the path to avoid the tall obstacles. Here's a little demo of it going. And you can see that the rocker bogie helps keep all 6 wheels in contact with the ground. For some of the results that we saw out of that testing, our initial observations were that it does work. Like the go command worked, it goes over the obstacles, and it does successfully use all of what we gave it. Some of the challenges that we saw with our first phases were the connection between the motors and the wheel had snapped. This is called a horn, and it snapped because it was plastic, so we switched to metal ones, and it did better. And the differential bar also was not fully holding the weight of the housing, so adding additional fasteners helped keep it tight and keep it steady, and it is currently standing. Moving into our budget.
Yeah, so for our project, we were given $3,000 to work with, but we only needed to use $2,026, so I think we did a great job.
Now going into overall recommendations. So in theory, if we were to have more time or if we were to pass this on to another capstone team, we would recommend these things. First of all, adding more sensors for, once again, sensor redundancy. So if something goes wrong with one, you still have points of data, as well as just more accurate information. Switching to DC motors for specifically the continuous rotation servos for one, getting rid of that horn issue, as well as having encoders for additional odometry. We'd also replace structural materials as we did, once again, see the horns breaking, specifically the plastic ones. So making sure to replace with stronger materials such as metal, and switching to a PCB design for a cleaner and condensed system, specifically for the power system. Finally, we'd also recommend having parallel workflows where, for example, in our team, we have mechanical engineers, electrical, and computer engineering. So for mechanical, finish a prototype quickly, hand it off to the next group, and then we could work on that prototype while they're already working on another. So keeping that parallel workflow.
Yeah, so some considerations for a space-ready version. We need a material switch to maybe aluminum, and then also have some radiation-hardened electronic components that are space-ready. Then just like making sure that we're ready to deal with extremely low temperatures and low gravity, as well as making sure cold welding isn't an issue. Cold welding is when metals fuse together in space due to a lack of an oxide layer, so we just want to avoid that. Some sensor redundancy in case any sensors break and we won't be able to see what's going on, so we can make sure that if that breaks, we'll have another to take its place. And then just solar panel for power, because when we're not up there, we can't just replace a battery. Here are our references, and we'd like to open the floor any questions.
As of currently, that's not integrated, but we could easily add that as code for if it's since there's constantly instructions coming through, we could add it to where if it doesn't receive instructions for a certain period of time, then to stop altogether, because currently it would be continuing moving from that last command.
Yeah, I think the whole design makes a lot of sense. I think there's a little trade-off in the coordination because now you do two systems, which makes it a distributed system. Thank you.
Did you use continuous rotation servos for the wheels?
Yes.
We have 6 continuous rotation and 4 directional for the 4 corner wheels.
I'm curious, in your research, I just quickly looked it up, so the mission is actually gone.
Yes.
And do you know, what are they sampling? What are they planning to sample when they reach the asteroid?
So for this first one, they're sending just an orbital, and it actually just did the thing, like a gravity assist past Mars. So it gets a little more power going off of that. So for this first one, it's just gonna orbit it, just scan it, so they won't actually be landing. And so that's where our project comes in to be like, oh, what if it did land the next mission? So just sampling what it looks like to get a closer look, what materials they'd be dealing with, and all that.
Yeah, what kind of gravity does the asteroid have? I imagine it's relatively small.
Very, very little. If Earth is at 9.8, they're at 0.01, 0.1, 1.6. 0.16? Excuse me, 0.16.
How do you keep it in contact with that as you go over the bump?
Yeah, so there's quite a few things that they do for that. One of them is to make it kind of springy so it almost bounces across the surface versus needing to stay in contact. I'm sure they use different type of wheels, but we don't necessarily know this asteroid very well, and it's full metal, and so maybe something like electromagnetic could work, so unsure.
So, you guys use 2D SLAM for the time constraints, but hypothetically, if you guys had time to implement 3D SLAM, what benefits would it give to your solution compared to the current state right now, specifically in your guys' project or problem statement?
So 2D would be, like the use for 2D here would mainly be avoiding walls and higher objects, but it'd be good to have 3D to see smaller objects and things that potentially the wheels could get caught onto. So having 3D would be good to basically avoid that. So path optimization to avoid those specific things that are objects that are in the way.
Would a vehicle like this be used primarily for mapping the area, or would it actually collect samples?
With the way we have it built, it'd be for mainly mapping, but I think there's other capstone teams at different universities that are also working on like sampling.
We have time for one more question.
Helene.
What was your favorite part about the project?
The final result.
I've never worked on an interdisciplinary team, so it was kind of cool as seniors for all of us to have brought the skill sets that we've built to do it, because it was like, Gina would mention something, I'd be like, I have no idea what that is, but Norelli would know what that is, and like Nick and I would do that with mechanical things, and so it was like a weird mesh of everything. I liked it.
All right, let's give it up for interdisciplinary. Could I have interdisciplinary team 5 coming up? Thank you.
Devin, I don't have access. You don't have access. Oh, wait, Austin. Could you give her access? Or do you want to sign in? Yeah, or do you want to sign in? Like, I don't. No. It's private.
It should be to whole university.
I requested access. It should show up in your email.
Whose email is that?
It should show up as
Oh my
like.
god, it's
oh,
owned by
wow.
Devin.
You could just plug that in, I bet. Oh, wait. If you copy link.
So,
Okay, yeah.
email?
NITYA. Yeah.
Let's try
But I
again.
think
Try
that
again.
might be
Try
what
again.
Devin did. If you go into this one,
Everyone should be able to access it. That's why.
okay.
You're using your school account, right?
Are you the presenter?
Yeah.
Oh, yeah.
Yeah, but they have technical issues right now because we're supposed to have that computer all loaded up for us, but
You're supposed to have that computer?
yeah, we are supposed to have all the site loaded up for us by the session head. But
To have access to the
Yeah.
Zoom? Yeah. Well,
yeah.
can you tell
Even
me?
to the
I can give
presentation.
you co-host access
can you? But
because I'm the
it-
technical monitor, but
oh,
you need to give me your email.
it's too late. It's fine. It's fine.
I talked to whoever was in here earlier, the main, like the setup guy. And then,
Which one are you? Which Zoom account are you? What's your name? Austin?
no, it's good.
Oh, no,
It's
it's good,
online.
it's good,
It's
it's good, it's
online. Like, same.
But you might need to do it with the last one.
I mean, I usually be doing with all of them, but you need to reach out to them.
Yeah. But you might want to try to find the last one.
Hello? Hello? I feel like that's bad. You gotta kind of hold it closer.
Alrighty, this is Interdisciplinary Team 5, Psyche Mission Origami Robotic Exploration. You may begin.
Hi everyone, we're Team INT 26.5 and welcome to our project on the Psyche Mission Origami Robotic Explorations. Okay, so here's our project team. So we're integrated mixed teams of mechanical, electricals, and computer engineering. And then we have Austin Lowe, he's computer engineering. I'm Shuzhao Li, electrical engineering. And then we have Devin Riley and Bright Schaff from mechanical engineering. So for our mechanical engineering faculty advisor, we have Dr. Mohsen Dafarniat, and we have Dr. Cassie Bowman for Arizona State University, NASA's Psyche Mission Liaison.
All right, so just in case you missed the previous presentation, Psyche Mission is sponsored through ASU and NASA. It is the space mission to the asteroid Psyche, which lies in between Mars and Jupiter. It is primarily made up of metals, so it is compositionally very similar to Earth's core. Thus, further research into Psyche could help us to further understand our own home planet. All right, so two major obstacles that are presented by surface traversal of Psyche are uneven terrain and varied surface composition. These are very common for asteroids due to low gravity and surface collisions with space debris creating craters. As you can see on the screen here, this is an altitude map of Psyche. These blue areas are the lower areas, with the red areas being the higher areas. In these blue lower areas, dust tends to collect, while the higher areas tend to be a lot more rocky. This makes the surface composition of Psyche just as uneven and varied as its terrain. All right, so given these complications, our sponsor has tasked us and the team before us with the task to explore and design a rover that approaches these problems. So given this task, our team has decided to focus our research into origami robotics. So what are origami robotics? Origami robotics, much like the name suggests, is a emerging style of robotics that focuses on the foundations of origami folding in order for a robot to move. Our team was really interested in origami robotics for a lot of different reasons, one of which they're just really cool, they're unique, they haven't really been done very much before, so we're like, oh, this could be fun. And then also just for actual space application, they have a really large range of motion due to their folding capabilities, which makes them more dexterous when approaching problems presented by uneven terrain. And then they are often very thin and compact, which makes them more lightweight, which is better for payload, and that's always good for a space travel mission. Over here, you can see the Mori 3 origami robot. It moves around using hinge-based motion. It's pretty cute. All right. So these are two different examples of origami robots. Closest to me is an example of a soft origami robot. It has a soft plastic outer shell, and these kinds of robots often use heat or electric signals in order to actuate motion. Furthest from me is an example of a motor-based origami robot. These are actually segments from the previous slide of the Mori 3 robot, which uses the motors to create that hinge-based motion. So our initial design used 54 of these triangular segments, which gave us a huge range of motion and would allow us to really address the issues presented by the surface of Psyche. However, for one of the main reasons why we were interested in this is that it was unique, it was cool, hadn't been done a lot. Also presented drawbacks, as there wasn't a lot of background research that we were able to pull from in order to create this fairly complicated design. And so what we determined is that we were going to focus on the basics of motion, really drill down into a simplified proof of concept design in order to further research in the future into this for future teams on Psyche. So this was our very, very simplified version of what you just saw. This is a 6 square segment design with all of them laid out horizontally. These then curl up into a hexagonal shape as shown here, and then they flatten out for one full cycle of movement.
Yeah, so now I'm going to walk through the features of our robot. So first here we have a SolidWorks render, and that we 3D printed using PLA. PLA was chosen because it's lightweight, relatively rigid, and easy to work with, which made it a great material for prototyping. When designing our chassis, we came into a couple problems, one of which was weight. How we solved that was adding cutouts into the chassis, which helped reduce the weight, but we kept material in non-load bearing areas to support the electronics and other features that we needed. So here I'm showing off the hinges. These are what connects each of the segments together and allows it to do its motion. Without these hinges, they wouldn't be able to link together in that line. And then here we have our spur gear, which we have integrated into our chassis. This is actually what allows for the articulation of our rover segments. And then here we see our motor, which creates the torque necessary to be able to rotate each of the segments and articulate them. On the side closest to me, you can see our motor housing. That secures our motor and restricts movement when it's under load during operation. And then on the further side, you see our dovetail, which is how we secure our motor housing onto our chassis. We chose a dovetail so that we can add and remove the motor housing when necessary. On the side closest to me, you can see how that slides on there, and on the further side, how that final connection looks. And then here we have a video demonstrating how that works.
So for electrical system designs, from our left, we can see that first we have the electricity plugged into the Raspberry Pi, which works as the main controller. So the main controller is going to send commands to the PCBs, and the PCB can start controls the motor. Once the motor rotates, it's going to start moving the segments. And here we just have another version views of it, how it looked like when all the components were on the segments. So on the left in here, we have the first Raspberry Pis. So it's going to send commands to the PCB, and the PCB can start controlling the motors. So the motors are going to start rotating, and it's going to rotate the spear gear right there.
All right, and this is the centerpiece of this project. So we have built a custom PCB for this project. Our electrical engineering team have designed this custom PCB by ourselves. It is manufactured in China and is assembled in US by ourselves using the machinery we have on campus. And this PCB looks really complex because it is, so we will just go through some of the major components on this board. So of course, we need to move the motor. So we have the motor controller. This one is actually a PWM-based motor controller. So it's something that is easily interpolated into some standard way of controlling motors, and it just controls the movement of the whole robot. Second, we have the data transceiver, which is a campus transceiver in this case. It takes in the differential signal from the main controller, and then it's transferred into something that the microcontroller can read and use. And last, this is the brain of the board, which is our microcontroller. It just controls everything, every IOs, every motors, and every data transceiver that is needed for this board. I chose this STM32 for this board instead of something like 80 mega because a 32-bit microcontroller is more versatile and it can handle a lot more processing compared to something like an 8-bit controller, like an 80 mega would be. And at last, we have the Raspberry Pi, which is sending the campus signal to the board to control the movement of the robot. And this is the overview of the control system. So we have the main controller sending out the signal via the campus wires to each of the board, and when each of the board receives its own respective signal, it will move accordingly. And this is how the motion control works. So we have a panel that we can select however many angles we want to send, and then when you click send, the robot will just move accordingly. And for our motion control, we have chosen that the positive axis will be going up and the negative will be going down.
All right, so this is a close-up of how our hinging motion works. As you can see here, just kind of a pretty simple hinge. Just as a little background as to what that 90-degree angle is doing, one of the major complications we ran into during this project was weight reduction for torque. DC rotational motors don't provide a ton of torque, and we found that we really needed to work on weight and reducing the amount of force that was being applied to that motor. And one of the ways that we could do this is by changing the angle, which is what that 90-degree is doing. Here is a 3D animated CAD model for our animated proposed gate, how it will move. It starts flat, rolls into that hexagon, and then flattens back out. And then it just keeps doing that in a cyclical motion until it starts going across the floor. This is a full-scale motion visual of what was just shown, real-life version of that. Unfortunately, this is an animated version and not real time, partially due to material degradation. PLA is a very soft plastic, and over time and overuse, it starts to degrade, which would lead the gears to not be able to rotate in the way that we wanted them to and fully propel into the shapes. So we had to manually help it to get into the angles towards the end there, which is what you see. Can we play that one more time? All right, as you can see, just same sort of gate as we proposed in the first part. Yay! All right. So in conclusion, while we faced a few different setbacks with weight and with our material selection, we believe that through our team and through teams in the future, origami robots will be seen in space and on asteroids in the future. All right, that's us on Psyche with our dog that we found. All right, any questions?
Did you ever try it on an uneven surface to see how that concept would work?
Unfortunately, so our design, because we simplified it so heavily, it wouldn't actually work on uneven terrain. However, research that we've seen and with the style of, when you have a lot of segments, you can sort of mesh to an environment, and that would be kind of how it would approach like rocks and stuff, or with having that folding motion, it could be able to roll around pretty easily when it would need to, but we didn't try it with ours.
You mentioned the PLA degrading over time. Do you have any ideas about what you would use instead?
Yeah, what we would probably use would be aerospace grade materials with aluminums or polymer-based alloys. Yeah, PLA definitely would not be ready, even temperature-wise. It was not space ready, for sure.
Do you think you are more constrained by the power of the motors or the strength of the gears?
Definitely power of the motors. I think that the strength of the gears, with gear ratios, there's only so much you can do and how big and how different you can make them while also trying to keep it compact. What we really valued keeping it fairly thin, and to increase that gear ratio any larger would make it to start getting really bulky.
Well, I think because this is pretty much a novelty design, we need to develop all the hardware on my side, especially the ECE side. I need to develop all the hardware and the software by myself, which takes a lot of time, and therefore that's why this product is at a research stage rather than a complete state.
If it just moves in a straight line, could it like go backwards or turn?
This could. It cannot turn, but it can go forwards and backwards. That's part of the reason why we used the squares instead of the triangles. Squares just really, really simplify everything to really try and fine-tune that basic motion of forward and backwards before going any more complicated.
I was wondering, do you have any concerns about how surface debris like sand or I guess regular would impact the machine because it folds close to the ground?
Yeah, one of the things with gears specifically, one of the things we were kind of nervous about would be sand getting within the gear teeth and breaking that. But one of the ways that people have kind of tried to mitigate that is by building either soft coverings around the gears or in soft coverings around the electronics. Did you want to talk about?
Yes. So there's some idea proposed that we can put a really thin, maybe a few hundred micrometer of material in between the gearbox, so it can still have contact to the surface, while at the same time that it keep the integrity of the part without like the sand will not get in.
Was there anything in your research as far as an origami style robot? What sensors and environmental awareness do they have?
With the robot being that thin, some of the basic scientific instrument can be there. Like for example, any type of like infrared meter or a temperature sensor can be on the robot. But if it involves something like digging and then sending the sample back, this won't be as suitable. This is more suitable for like a scout mission to the Psyche asteroid, and then when we find it is suitable for further research, then a bigger rover could be sent over for the actual big task.
The other really cool thing about origami robots in that capacity are because they're so lightweight and thin, you can send a whole bunch at a time and basically send a swarm of origami robots all at once. And this is actually a thing that NASA and other companies have kind of been thinking about, is this sort of swarm robot style of,
One more question. Do you know if anybody dealing with the mission ever thought of something like the BB-8 robot that's on Star Wars?
I feel like BB-8 would fall over. BB-8 would fall into a rock. No?
No. The head is actually disconnected. It's not hard connected. It's connected by magnets, so it floats.
Oh, interesting. I haven't heard of that, but that's something to look into for sure. Huh. Have you guys?
Could we have CS Team 3 up here? Okay. Is it your laptop that you're going to present through?
Yeah.
Okay. And you are, sorry, I don't remember your name.
I'm Jada.
Jada. Okay. I'll give you co-host.
My professional, bro.
Did you want to connect yours? It'll take the Mac or the USB-C too.
Okay. You should now be able to present.
Okay.
And I'll come grab this after the session, so it's not.
It looks complicated. Because
Yes, it is. I was
I was like,
like,
yeah, you tell him, bro. You tell him.
dude, are you leaving?
Yeah, I'm gonna go check out the other PCB project.
We should stay. Unless they stay for us. Oh, I was hoping the crowd would be gone. There you go. Let me make that go away.
You know these are clickers, right? Yeah, you can use them to advance through the slides, and also it has a this. So just so you know, I believe it's a remote, so if those should cause the slides to move forward and back. Do they? No?
Isn't it like a USB dongle or something? We changed computers, so.
Okay, that might be it.
It's okay.
All right. Yep, more time. All right, we have CS Team 3, FLOATVR Mobile for Brainswitch Labs.
One, two. I think we're good. Okay. Hello, everyone. It's great to see you all here. Thanks for coming out to take a look at our project. I'm Cole Pack. I am joined here by my team, Antran, Owen Abbott, and Jada Ruzak. And we're working with Brainswitch Labs to create the app FLOATVR Mobile, which is a mobile app that's supposed to promote mindfulness by putting you into a unique audio-visual experience and letting you just kind of float through the environment. So yeah, super excited to tell you guys about this project that we've been working on for the last 9 months.
Now I have to click.
We'll start with a quick intro to what the project is all about, move into a top-down look at all of the components that we worked on, then dive a little bit into the technical details of how we made it all work and how we put it all together, give you guys a nice little demo to show the app in action, and then close out with some ending thoughts on the project. So I'll pass it to Jada to start us off.
Okay, thank you, Cole. So what do you do when you need to take a break? You don't want to be bored, but you also don't want to be overly distracted. The problem nowadays is that there's so many things that are trying to grab and keep your attention for a long time that Brainswitch Labs' goal with FLOATVR is to be something different. FLOATVR on MetaQuest, the original app, has been shown in several studies to reduce anxiety, depression, and stress among several age groups. And our mission with Brainswitch Labs is to make those mental health and wellness benefits more accessible to people who might not be able to afford expensive headsets, as well as people who are able to but would like to float whenever they have the chance, or whenever they have their phone.
I'm sorry, which screen are you sharing currently?
My laptop.
This is what we're seeing right now. So, could you try sharing the other screen, perhaps?
Okay, sorry.
Don't worry, you'll be given extra time. We got some wiggle room.
Okay. Does that work?
Okay, we're good.
Okay.
So the brief from our sponsor in the beginning was to build a system, not an app, something modular enough so they can keep evolving on the design long after we hand it off. And that shaped every decision that we made. So we split the work into 5 pieces. We have the UI, which is what the user touches. The sequencers control the session timeline. The node graph is where the designer can create a logic for how an experience feel. And then we have the generator mapper and the audio mapper, which turn that logic into what you hear and what you see. So now Jada will walk you through the UI components.
Okay, thank you, So the FLOATVR mobile UI was basically designed so that the main neutral interface was as minimal as possible so that it doesn't pull you out of the experience. And the idea is that all of the controls, like all of these sliders and grids, are all tucked away in this bottom bar until you need them. And all of these sliders, grids, and 3D prefabs are easily modifiable due to them being defined in a JSON config file. And all of our FLOATVR mobile UI was built with the Unity UI toolkit, so UXML for structure, USS for styling, and C# for runtime logic. Now, the FLOATVR mobile UI has 2 main components, each owning their own document and lifecycle. The first one is the main menu where the user starts. As I said before, all of the 3D prefab planets are corresponding to each of the 4 modes: relax, focus, sleep, and energize. And then once you're actually in the session, the second UI component is the control panel. And that also has 1-dimensional and 2-dimensional sliders like the grid you saw before that are easily modifiable. And now Cole will talk about the sequencer when you're actually in the experience.
All right, thank you. So you go from the main menu, you click one of the orbs, and it starts off the experience with the sequencer kicking everything off. So the sequencer has 2 main jobs. It sets up all of the visual and audio components, and it controls when they actually play during the experience. So we can start with a sequence, which you can think of kind of like as a timeline, which says which visuals and audio will play, when they show up and for how long, and how long they spend fading in and out from the background when they enter and leave the scene. So from there, we move to the actual sequencer, which takes the sequence configuration based on the mode. It sets up visual prefabs. It sets up the audio system and the audio mapper, which is later going to be used by the node graph system. We'll get into that a little bit later. And it'll start computing what we call fade values for every visual frame. So as for what these fade values actually are, every visual and audio component has a fade value attached to it, which the sequencer controls, saying basically how faded into the experience should you be. So for example, for audio, this will usually control the volume, so it'll become louder as it starts and quiet down into silence as it ends. For visuals, we can have it pretty much affect anything we want in the actual shader. So usually we have it set to change the transparency of the object, or the size of it, or the density of the like if you have a big old field of little dots, you can change the density of it so it starts with just a few and then fades into many, many more. So yeah, the sequencer is the thing that lets the designers on the Brainswitch team create a full dynamic audiovisual experience. But it also works in tandem with the node graph system, which lets them define how a user can control their experience. And on here, we'll talk a little bit more about that next.
Thank you, Cole. So every mode should feel different, whether it's energizing, focusing, or relaxing. The question is, how would the designer can shape that feelings without having to ask us to rebuild the whole app every time they wanted to try something new? And the answer is the node graph system. The node graph system is a visual tool that let the designer to create logic of how a session of the experience without having to touch any code. And I have a very simple example node graph. To your left, there would be an input node named intensity. And this node is not a random node. It's actually wired up to an intensity slider that Jada made for the UI. And then the designer will feed that into a multiply node and multiply the value by 2. And then it will connect the result to an output node, which they have named speed. And the name here is very generic, and it is intentional because the designer doesn't really have to know much about the audio or the visual properties. They just give the output node some generic name. It could be complexity, or it could be colors, or it could be anything. Because on Unity runtime, we have 2 translators we'll pick up, one for audio and one for visual. So after the designer finished with their design, they save the graph, and it will become a JSON file. In Unity runtime, the node graph processor will evaluate the graph, and then it's gonna evaluate again whenever the user touch the slider, and the value that lives in the slider will flow exactly like the graph of it will be multiplied by 2, and then before it reach the output node speed, and from there it will flow into a two-way. The first one would be into the generator mapper, which is the visual that you can see, and the other one would be going into the audio mapper is what you hear. And Owen is the one who does the visual piece, so I'm gonna hand it over to him.
Yeah, so the node graph defined what the session should feel like. This is the designer, right? They give you values like speed, complexity, density. But the generators don't know anything about these, or what this, sorry, the node graph doesn't know anything about the generators that it's affecting. So this is where the generator mapper comes in. It takes in the values like speed, complexity, density, and then using a JSON file, it maps them into shader properties. So you can dynamically affect what the scene feels like. The way this works is each generator has its own JSON file. And upon activation of a generator, the mapper reads this JSON file and then starts subscribing to all the variables that the node graph published for the generators, like speed, density, whatever. And then it will remap these inputted values into the correct parameters. So here we have complexity from the node graph, and it goes into the shader property, shape 1, wave frequency A. A little wordy, but yeah. So the generator mapper lets the node graph be very abstract and let the designer have a simple time to design. So an example of this, as we've kind of already done, is let's say there's a mode and there's 2 visuals that are active, 2 generators. There's these rings that come by and the blobs, right? So they work with the same node graph. They'll have the same inputs like complexity, intensity, whatever. But they get to map them however they want. So the rings might map complexity to how much the rings twist and how much they warp, whereas the blob field might use complexity to manage the drift speed and the drift range. So this is the architecture right here. Node graph outputs get mapped. And then, before finally sending the final values to the shader variables, the sequencer has sent us a fade value, and we use that as a multiplier to affect what the fade does. So maybe the fade makes the scene go transparent, or it makes the scene objects kind of shrink. So it's very dynamic. And now we're going to do a little live demo. Just laggy.
We have a backup video.
Yeah, it should be.
Yeah. Okay. Live demo not working. We have a backup. So here's the main menu. You can swipe through the different planets depending on what your mood is feeling like. And as I said before, any of these modes can be changed or modified or enabled or disabled. So if we take a second to go into Energize, can this play?
So, as you can hear, that was energetic music, right? Maybe we'll turn this off. As you could tell. And so everything is very dynamic. As you can see the visuals here, they're actually, we used a technique called ray marching, which shoots a ray from each pixel, for each pixel on the screen, forward, and then checks if it collides with a mathematically defined function. So right here we have toruses, and we can modulate this with like sine waves and time, and we have so many parameters that basically just go into a mathematical function, which makes the visual super dynamic. And also, as you can see here, Jada's now playing with this slider, and right now we're like messing with the parameters of the math. So everything is very modifiable. But it doesn't need to use ray marching. Literally any visual that has parameters can go into this system that we've built, which is our sponsor's intention. And you can see all the sliders there. So yeah, it's just, we built a system, and these are the current visuals and audio we have, but anything can get put in and replaced. And that's pretty much our app.
Cool. Should I share for the slide for reflections? Yeah. Okay. So, we are going to talk a little bit about what we took away from this project. Where is it? Sorry. So, one thing that we wanted to talk about that we took away is that we felt that our design flow and our project implementation throughout was just very unconventional. We hit our MVP around winter quarters, so from there on, the process was a continuous implementation with our sponsor designing the architecture and features in real time and giving us ideas, us building it, and then them telling us what to modify. So it was just really interesting to work with really responsive and skilled sponsors in a really dynamic and creative way. So that is what we wanted to talk about. Any questions?
Like the node graph, is that just for developers, or is that something that the user can actually make their own visuals with?
It's just for developers. Yeah.
This is currently what we're seeing. So there's not much to see.
It's just,
yeah.
I know.
But if you stop it,
Okay.
see the camera view. That's all.
Yeah, okay. Oh.
Yeah, I mean, only the designers can mess with the node graph, but On made it super like playable. Like we have a non-technical, really good creative, and he can just drag and drop whatever he wants. And then the UI does feed through the node graph, but no, the users won't be playing with the actual node graph itself.
I like the customizational thought you put into it. Kind of super excited about this. How would you see interfacing biofeedback into your software?
Whoa.
Exactly. Whoa.
Yeah.
And then it goes to maybe autistic, ADD, go on, answer that.
I mean, I personally haven't thought about that, and I'm assuming, have you guys thought about the biofeedback? But no, yeah, I think that is the beauty of this system, right? And that's the reason our sponsors wanted us to just make a system, not like, here are some visuals. Everything is so modifiable at every level, and it was really cool. We have a really good technical mic, and like we would implement something, and he's like, why would you constrain it in that way? Like, just make it a loose connection. And every part of the process was like that, and it was really eye-opening.
He could see like problems around the corner and then tell us what we should look out for.
Is Brainswitch Labs a startup, or do they have a product?
They have a product, so this is built off of, they have a VR product where there's like a subscription service, and they have active users, but they wanted to make it more accessible and maybe drive some people from mobile to the VR.
Yeah, they created FLOATVR on MetaQuest a few years ago, and they're basically a creative technical studio based in Vancouver, Canada. Any other questions?
Thank you.
Thank you.
Thank you to CS Team 3. In case you don't have the schedule handy, this is the last presentation for this session. We will be back in 17 minutes. So until then, go outside, look at the posters, enjoy yourself.
So where's everyone coming from today? We have 2 minutes. I know we have our okay. So maybe brief context. This session is our 2 p.m. Psyche capstone session. We have our 3 teams, 1, 2, and 3. We have a lot of computer science professors coming around. Some computer science students. Engineering. Where else? I don't know.
Really practicing your pattern skills is good.
Where are you coming from, Professor?
Bellevue College.
Bellevue College. Okay, welcome, welcome. Any other non-Seattle University people? In the
I'm a freelance consultant and a guest speaker at Mike McKee's class. So
That's right. Hi, Mr. Bach. And Mr. Bach.
Yeah, you were one of the people that gave us advice about how to make our game better.
Industry review. Yes. Thank you. We have over here in the blue jacket. Dropbox. Welcome. And Nintendo. Welcome, welcome.
I'm an old alumni.
You're an old alumni. Computer science?
Double E.
Double E.
There was no computer science in those days.
That's right, that's right. Did you teach any computer science courses? Back then?
Computer vision.
Computer vision. Oh, that's actually my favorite part of machine learning. That's what got me into the machine learning of the more recent pre-transformer computer vision things.
All right. Yeah, we are at. I did was well pre-transformed.
Well pre-transformed.
We're at 2. Hold the mic just a little bit, not too much closer, but just a little bit closer. I think we should be good to go whenever you are ready. Max is going to kick us off with a 5-minute intro for the Psyche mission, so that not every team has to repeat the same thing over and over again.
Yes. All right, well, good afternoon, everyone. My name is Max Trin. We're here with the Computer Science Department. And on behalf of myself, my team members, and my fellow Capstone colleagues, we are very excited to welcome you to this 2 p.m. session of Projects Day. This is room 110. All 3 teams presenting today, including my own, are sponsored by the Psyche Capstone program. And our agenda is threefold. We have our 3 capstone presentations and this brief Psyche introduction. I think starting with the why of the Psyche capstone, and welcome in if you wanna find a seat. Psyche capstone. Well, to get started, I have a few questions that if you could help me with some arm raising. Does anyone know anything about, if you know something about the Psyche mission, could you raise your hand? Raise your hand high. Ooh, we have some Psyche fans. So Psyche has a target destination and a way of getting there. So maybe, could you give us one of those?
Well, I only know because the previous session talked about it.
They talked about it too. Okay.
NASA's going to an asteroid out there.
NASA's going to an asteroid, that's right. We're going to an asteroid, and we're going to that asteroid with a spacecraft. But the really interesting thing is the story behind the Psyche mission, the story behind Psyche, actually starts here on Earth, about 3,900 miles below the surface. We can go over that one. With the idea of digging a hole to the core of our planet. Let's see. So, the average radius from the outer surface, the outer crust of the Earth, to the center of the Earth is about 950 miles. And the interesting thing is we haven't gotten very far. So if you decided tomorrow that you wanted to dig a hole to the center of the core to see how it worked, maybe you're interested in how Aurora works, or you're interested in just learning more about our planet. If you wanted to take a giant excavator and start going down, we haven't gotten very far. In fact, the deepest we've gone, digging-wise, with a borehole, a really small hole originally for testing out spots for mining oil. The deepest we got was 7.6 miles, 7.6 out of those 3,950 miles. And that was back when we had the Soviet Union. They were the ones who were actually trying this digging. So we haven't gotten very far. And the reason we have Psyche as the principal investigator of the mission for NASA puts it, is we want to explore our inner world, inner space, by going to outer space. So there's this asteroid, 16 Psyche. Based on what we can tell from looking at it from the Earth, we think it might be the core of an early planetesimal. Planetesimals are those little chunks of rock that have accumulated and formed that we think might have been the early precursors to planets. So Psyche is the core of what it might have been, what might have, in one other possible world, formed a planet. And so our hope is that by sending the Psyche spacecraft to the Psyche asteroid, we can learn more about the composition, the structure the way our Earth's own core actually works. So where are we today? The Psyche spacecraft launched in 2023, and it's a long journey. We actually, last month, last May 15th, we actually just passed Mars. This is a photo of Mars crescents taken by Psyche from this angle of approach. And in 2029, the spacecraft is on target to arrive at the asteroid. 3 years, 5 months. And where this brings us today is, in the meantime, while we're waiting for Psyche, NASA, in partnership with Arizona State University, has launched the Psyche Capstone Initiative. And what Psyche Capstone is for is to really engage the public, to build with student teams these types of different types of experiences, of games, of ways of promoting the mission, so that more people know about Psyche and are ready to be excited for the science that can happen when it finally arrives. The interesting thing is our project sponsor, Dr. Bowman with Arizona State University, is the interesting thing is Dr. Bowman has been running Psyche Capstone for a number of years. And this year, Dr. Bowman actually has 84 distinct capstone teams across schools in the United States. It's a lot of capstones. But the interesting thing is that there are so many parts of the Psyche mission that teams can focus on, such as there's the science tools, there's the trajectory, there's the ways teams have made Psyche work, as well as there's a system in place, the discovery mission system that NASA has that made this whole mission possible. And this is the part of Psyche that our team has really pulled off and is excited to talk about today. Actually, so if we introduce ourselves, my name is Max Stranigan. We have.
Hi, I'm Avery Feingold.
And my name is Christian Bonifay.
We're with team 2612 in the computer science, and our sponsor is Dr. Cassie Bowman, and our faculty advisor is Dr. Cuneo, moderating this Zoom session today. Thank you, Dr. Cuneo.
So, thinking about our game, we wanted to focus on discovery missions. And so Psyche is part of a greater class of missions consisting of 13 successful missions that all are low cost. Now, low cost in NASA standards is like $500 million. But what that means in practice is they're able to look into a variety of different scientific topics and explore the cosmos in ways where a bigger mission may not be able to. And even though you may not know these by name, you may know some of the notable missions, such as the Mars Pathfinder and Lunar Prospector. These missions have been integral, and this program has been going on for almost 30 years.
Yeah, so about the actual main game itself. This game was originally called PSYCHEOPOLY because it was just a reskin of Monopoly. Because we actually had basically unlimited free reign on whatever we could do, we decided that to just reskin Monopoly was probably a bad idea because this was a game aimed for younger kids. And if you know, Monopoly is very, very long. So we decided to incorporate a game which a lot of kids are familiar with, Mario Party, and take some of the aspects and elements of it and put it into this game. So the game it runs on a board, but you also have mini games. And this was actually pretty helpful for us when creating games because it allowed each developer to basically have full artistic control over their own game while not having to develop the full game themselves and having a limited workload.
And so thinking about the audience, we really wanted to create a game that was tailored towards younger children. These are the children that will be the forefront of people who are going into NASA or getting interested in space, and we wanted to engage them, specifically with Psyche for the program, but also with discovery missions in general. And so we decided to make a game that was about engaging them by making them think about what it would take to build their own discovery class mission, get it approved by NASA, and go through all that to get their own scientific research and discoveries out into the world.
So our inventory system, this is the main part of the game, and because we have mini games, we wanted to have something to tie everything together. And so we have an inventory system, and in it we have a bunch of items, and your goal is basically to collect the items to complete a quest and to win the game. Now, with each of the items, because this is a game that should be for educational purposes, each of the items are related to this discovery mission in some way and have a little bit of a description about what the item is and what it's for.
So now moving on to architecture and design. We developed this game using the Godot game engine, which is an open source game engine. We thought that would fit student projects since it's continually iterated on and it hopefully won't shut down anytime soon. And then we're delivering this game to our project sponsor, Dr. Bowman, in a monolithic architecture. So we are delivering it all in one file, all in one place, so no different places to look for files. And then Godot uses scene-based architecture, so our game is composed of scenes that utilize scripts to help tie everything together. And for development, we use pull requests. So each one of us would create our changes in our own branch. And then another developer would review it, make sure it plays well, and then push it to the main branch. For playtesting, we originally tried using unit testing, but we found that that was a little slow for how fast we were developing and making changes. So we moved to playtesting so we can get everything done quicker. So some challenges we had. Originally, we all worked in the main branch, so everybody's working in one place, making all their changes in one place. That ended up causing everybody to overwrite each other's changes. That caused a lot of problems. So we, as I said before, we moved to pull requests. And then now, we'll start running through the demo.
Game demo. All right. So as we like to put it, our game is, the goal of our game was to combine sort of Monopoly style movement and resource collection mechanics with Mario Party style mini games. Let's see, and sort of now that you've heard a little bit about the architecture of the game and the pieces we were trying to put together, what is the story? What is the story of the game? So through our game, if you, I don't know, if you have the audio, through our game, you play the role of a scientist, a principal investigator in charge of your very own discovery mission. When we start, and so the goal of the game is to collect your science instruments, to collect your resources, and build your team so that you can get your mission off the ground. So here right now you can select from a subset of the 13 flown discovery missions. You can choose which one you'd like to build. So you can play around with the tokens and select a mission.
And so for our game, we really wanted to make sure that we're making a gameplay experience for younger children who may not have played more complicated games that's easy to understand. So we created a tutorial and also added in a lot of those story elements that Max talked about in a way where we're continuously reminding the player what they're doing and why to stay engaged. Through this, we also are able to explain more and give the player a stronger sense of what's happening in the game. We also wanted to create a game that was engaging. Now, engaging game is one that has replayability and has player choice. So what we did is we created some quests. Randomly at the start of the game, some quests were generated, and the player's goal is to complete at least one of the quests before the game is over. In this way, we create a game that's going to be engaging for the younger audience, while also having replayability that's needed to keep people playing.
So this is the main board, and this is how you interact with most of the items in the game. You have two buttons. You have a button for the inventory, which holds the items that you can gain, but we don't have any items now, so we'll show that later. And then you also have the button to move your character around the board. Now, there are several types of squares on the board. The first one is a chance square, and through here you can gain or lose random items and money. And if you open the inventory, you can see that it has indeed added an item into your inventory, and each item comes with stats and also a price that you can sell it with. So if you want to buy other items, you can. And then there's minigame squares. And so you have a prompt if you actually want to play the minigame or not, because you don't actually need if you don't need the rewards from it, then you don't have to play it.
The original idea was we have a series of mini games that players can play, each focusing on different discovery missions. This one is based on the 2001 NASA's Genesis mission, where you collect solar ions. What were we going to say? Yes, in this game you collect different ions and bring it back to Earth in your sample return capsule. maybe an interesting feature is originally our team was in talks to develop multiplayer gameplay. And this scene, along with the introductory vending machine scene, they were originally designed with multiplayer tiling so that different players can select their options.
And then this is the shop screen. This is where you can take your money and the items you buy, and you can either sell the items that you want to try out different ones, or spend the money you have earned and try to buy items. Now, when you hover over each one, it lists the description of the item and the price that you can sell it with. And so if you buy a couple, right? And then the sell button also duplicates as your inventory, because you can go into here and you can also sell the parts that you have in addition to looking at what you do. And so the parts, you can select multiple parts, and then there will be a total at the bottom to if you want to sell them or not, and then the cancel one will deselect all the items that you have picked.
And one key piece about this is that we wanted to implement interaction or knowledge of the player. So what we do is we have little things about each of the items, which are each based around different discovery missions, and each are different parts. And so players are not only learning about discovery missions, but they're also getting to play our game. And so, oh yeah, thank you. So this minigame here is the alien communication minigame, where players try to spell words to communicate with aliens. One fun thing about this minigame is that it was made using a trie structure, where it is a tree, but where every single branch contains data. But you have a limited time, and if you don't make it, oh no, okay. We didn't complete the minigame, but we still got time to win.
And so this is our third and last minigame. This is the asteroid targeting minigame, and it's based off of the NASA Psyche mission. So the goal of this minigame would be clicking on the Psyche asteroid as it bounces around the screen. This is one of the minigames that we designed for more younger players, so it's easier for them to complete. And so there are 3 stages. It transitions through different backgrounds and different screens that depict, well, outer space. And then as it progresses through the screens, more things will pop up, and also the Psyche asteroid will speed up. So let me just click through here. It'll bring you to the end screen, and then back to the main board.
Yeah, and then you also have this, there's also this feature which is branching, and you have 2 options. You can either pick to go in a different branch, which is indicated by the blue squares, or you can still continue along on the main board. And this was just designed to give the player a little bit more options in what they wanted to do.
All right, well.
Yeah, so I think that's it for our presentation. Is there any questions that people have?
Were you able to test it on people?
Yes, so I work at a high school, so I brought up a big smart board, just put it in the library, had probably 100 play testers throughout a week. Yeah, so they gave us a lot of feedback, and then they helped us give us feedback. So we redesigned the main menu like Max did, and so that we used a lot of that.
Out of 5 stars, what did they say?
I'd say 4.5. They'd like more mini games.
That was actually an interesting feature of sort of our original vision of the game was to have more features and more parts of the story built in. I think an interesting thing we've all discovered as we worked on the project though is like as you work with these modern game engines, it does take a while before you're comfortable making things in them. And so
And also, developing a game is not just a thing where we're given some boilerplate of what we're going to be following. So it takes a lot of messing around in the pig pen and figuring out what we want to do creatively. And so we had many ideas, and part of this process was not just making things, but also figuring out how we're managing our ideas and forming one cohesive narrative.
And I think we're at a point now where if we were starting to make the game now, we'd be able to do more pieces since we've gotten some experience now. Okay. Other questions? Thoughts? Rena? Oh, sorry.
If you have
So you're probably familiar, but the way we've been practicing developing over this year is the agile method, where sort of you respond to things and you update your plans as you go along. And sort of the way we developed it is we sort of had, we had the board MVP, the minimal viable game, with a collection of mini games. And more recently, we've gone back and have started working on the introduction scenes. I think if we had more time, I think we'd keep going through that revision effort of, there's a lot more to put in on the story. We do have more mini games, and pulling pieces visually together is visually together with stories.
And I think our goal here, right, thinking about this Mario Party idea, is a bunch of really short, quick mini games that give the player this kind of almost frantic, excited sense. And so if we were to have more time, and we've also added in the structures, so if another team were to want to go into it, or us maybe later, they can add many more mini games and make this feel much more robust.
For me, to extend the game a little bit, I would probably move quests. I would have quests and out of like final goals, and so that since the game would be a little bit longer, you'd have these quests in between as kind of checkpoints to keep the player engaged.
Got time for one more quick question.
So your sponsor hasn't seen this yet, right?
She's seen it.
She has.
Yeah,
She has. Okay.
Dr. Bowman is in Arizona, at Arizona State University. So through the past year, we've been meeting virtually. I think things are a work in progress. Things can always be added in, but this is where we're at the moment.
All right, well, thank you all so much. Let's get our next team to come on down.
Come on, bro. You should now have co-host. You should have co-host submission now, so you'll be able to swing the
And just make sure whoever is talking, microphone, not super close, but still pretty close, right? If you want to gesticulate, use your other hand that is the microphone holding you. Any questions about what you're going to do?
Hold it right here.
About there, yeah. And if you're doing the demo, maybe have someone hold it for you.
I'm guessing, yeah. So do I screen share?
Hello? Oh, okay. We're gonna get started. Hello, everyone. Thank you guys for taking time out of your day to come to our presentation. We're really happy to have you guys here. We are yet another NASA Psyche capstone team. We are 2616. My name is Lauren.
My name's James.
My name is Ani. And I'm Johan.
Yeah, and we'll go ahead and get started. Just to recap what Max kind of talked about, our project is centered around NASA's Psyche mission that is in partnership with Arizona State University. And so basically the Psyche mission involves NASA sending their spacecraft to this asteroid named Psyche, and they believe that this asteroid is comprised of metallic components. Typically, asteroids are made of, are more rocky or icy, but this one in particular is very important because it is mostly made up of metal. They believe that it's iron and nickel, but they have yet to discover it, so that's to be determined. But they believe that this asteroid will tell us a lot about
planet formation and things like that. So kind of what Max already iterated. So our specific challenge was that space missions can be difficult to visualize and engage with. Obviously, we didn't know too much about the mission going into this, so I assume that you guys probably don't really know what to visualize as well. And traditional learning methods are often passive. So in the past, NASA has created 2D games such as like ones before, but ours is specifically special because it's virtual reality. So this way, users can physically explore the asteroid environments in a 3D environment. So overall, our goal was to create an immersive virtual reality experience that allows our users and players to learn a little bit more about the metallic asteroid Psyche in a more interactive way. And then I'll pass it to Ani for this.
Okay, so this is our core gameplay loop. So basically what we have you do is we have you in space, and we have a model of the Psyche asteroid in front of you, and we're basically giving you a camera. And this asteroid is like moving around, and your goal is to take pictures of things on the asteroid. So you can take pictures of like craters, different metals, and we will score you based on what you take a picture of. And at the end, we show you all your pictures in like a discovery book, and it tells you what you took a picture of. So you can see things, take pictures of them, and then learn about what you took a picture of.
Yes, so to kind of deep dive into a little bit more from what that high level explanation was, we have 4 main key features for our game. We have first our interactive camera system. So we have a 3D camera model for the user to interact with, and this is how you'll be taking pictures. The camera has a collider system that kind of hits different objects on the asteroid as it spins, and from there it'll validify if that object is scoreable, unless it's just like a spot on the asteroid. And with each object, they correspond to a different score, score number, and things like that. And then that brings us to our dynamic heads-up display. And so the user can easily track the amount of film, score, and time that they have left in the session. And to kind of reiterate, the goal is to capture as many pictures and accumulate as many points as you can before either your film runs out or your time runs out. And so moving on to our object detection and scoring, once your session is over, it'll prompt you that it is over with your score, how many photos you took, and the reason why your session ended. So like I said, you might run out of film or you might run out of time. It'll tell you. And then at the bottom, you can have the option to view your specific discoveries. And so we have this discovery log for each object type that you can look through, and it'll tell you a little bit about what you took a photo of. So let's say you took a photo of an iron composite, it'll tell you its relation to the Psyche mission and why it's so important. So yeah.
So looking over a little bit to our tech stack, compared to the last project, we use Unity and Zenfido because it includes a lot of XR and VR toolkits that help us build our game more efficiently. And it also has a lot of different scenes that we can put our environmental noises or just backgrounds that can make you more immersive, that makes you feel like you're actually in space. For the 3D modeling, we use Blender. We have thought of using Maya, but then since we are all new to all these 3D modelings and development process, so we decided to use Blender as in it's more beginner friendly. All the asteroid models, the little rocks, the camera models, or we have like the little spacecraft tunnels that we have in our game are all imported and created in Blender. As in version control, we use GitHub. Just like last group, we use pull requests. So all of us, as we finish an update, we have one another review it, and we have a list of what we go through because of how we created our game. We don't usually use unit testing or auto testing. We just play test the game ourselves and try to break it as much as possible because that's what people do, right? And whenever things are right, doesn't seem like there's any bugs or errors, we'll merge into the main branch and continue to the next script. Next slide, please.
Yeah, it's during the developing, we face many challenge, and we have the to refine the project through the interactions. One major issues we face is the VR user interface. At first, too much information appears on squares. At the same time, it was makes it difficult for a player to read and understand where were the VR high sides. And another challenge was limit the high size. Since not everyone can test in any time, it slows down our testing the process. And some of the Unity XR the interactions also require the repeat debugging, especially the like the player's movement and the promote and for sorry, it's okay. And for the controller, the basics, the interactions. And we mentioned that the timing and available for the promote need to be improvements. So how to solve this the problems? We split the large control panel into a smaller step-by-step promote tutorial, and it makes the controls easier to read at one at a time. And we also adjusted the promote to appear based on the player's locations and process in the games. And another important iterations was discover books. At first, we wanted to provide the useful mission information, and we didn't want it to interpret the gameplays. So we improved this discover book layout, and we use it to give the object descriptions and the missions directly.
All right, let's move on to our fast demo. Just a little run through on what you will see in the game. Let me see if the audio is right. Okay, game is over here. You mind pressing start for me? Hey, I'm gonna be a performance in front of everyone. Laugh at me. Oh, did you start?
Wait 1 second.
The
Make
play
sure to hold
button.
the microphone up to whoever's talking, even if it's in the way.
Let me try to hold it.
Yeah, there you go.
Yeah. You're gonna hold it for him. Did you click play? Oh, it's loading. Or are you just gonna?
It's the joy of Unity.
Yeah.
The superior Godot wouldn't have this problem.
The superior. Find Unity taking 30 years to load and it crashed.
It just cost us 5 installs.
Yeah. Well, we used to know. We did vision this. We had like a future sphere.
So we have these robotic hand models to make you feel like you're in the future. You can see our title, NASA Psyche VR Exploration, with these very immersive background. You can click on About. That's going to show you the disclaimer and all of us as the production team. I'm just going to start the game real quick. So you're going to get prompted by this little control panel that tells you what to do and what each button does what function. And then it's going to tell you who you are, why are you here, and what are you going to do. So you're just we're trying to mimic the process of the Psyche mission of the spaceship scanning the Psyche mission. But instead of using scientific tools, we use a camera so people can relate more to that part. So in order to move, we have this teleportation movements where you have this indicator and then it teleports to wherever you point at. And once you teleport to this anchor, it starts the game. We can pick the camera, it's dynamic, you can spin it whatever you want. It's gonna stay mid-air, you can rotate it whenever you want. So what you're gonna do is you're just gonna point this camera at like these metallic objects and then press the trigger. You're gonna take a picture and then it's gonna show on the left side what you just took. And then you can tell the film just went from 20 down to 19. The time's going down and then you got scored with 15 score because you took the picture. So I'm just gonna take more pictures. And then just in case you need to use the bathroom, we have a pause menu for you. So it actually stops the timer and then everything just froze in time so you can take care of whatever you need to do and then you can resume the game whenever you want to. And I'm just gonna spend more film, taking more pictures. As the film goes down, the HUD changes color to kind of remind you you are running low on films. And when you run out of films, it says mission over. I got 230 score with 20 films taken. And then if I press this button over here, it's gonna prompt you with the discovery book we were talking about. And hey, I captured a nickel. And then why is it related to Psyche? I don't want to read that in front of everyone. So it's going to be in the game. And next page, we found iron. Next page is a crater. And then whenever you feel like you're finished reading everything, it's going to press another button. It's going to bring you to the main menu. So I'm just going to look around because this is the spaceship tunnel that we kind of build, so you feel like you're in Star Wars. That's pretty cool. And I'm just gonna press a button. That'll just bring us back to the main menu. So we actually made this game very short and fast on purpose because NASA did mention that this game, if it's well enough, will be shown in the events, and then we want more people to contribute to it. So we don't want like a 20-minute game and it's just gonna crowd the booth. So that's our little demo.
It's lagging. What? Okay. Yeah. Just to quickly conclude, this is our project. Our goal is to inform and educate people about the Psyche mission using a fun and interactive VR game. And I think we created a really good product that's quick and fun and informative. So thank you for listening to our presentation.
Do we have time to take questions?
We have 5 minutes to take questions.
Any questions? I guess. Oh, please.
You know what? I'm seeing like you have taken like a bunch of same picture. How the program identify like the difference between what I have taken?
Okay, so it's actually pretty neat. We actually don't score you if you take the same object twice. So as Lauren was saying earlier, we have this hitbox that actually captures the object whenever you click the trigger button and then saves the object ID into a backlog. So whenever you take the same picture, it's gonna identify, oh, this object is already in the backlog, so it's not gonna score you.
I see.
Yeah. Please?
So mechanical engineer, not a software person. Comment, thanks for the nod to old-fashioned film cameras.
Thank you.
But it's usually 24 roll or 36. pictures.
Oh, neat.
To know.
Not
Good
30
to know. 24 or 36.
But how difficult would it be to extend and have the person like be able to fly and go around the asteroid and then take pictures like on all sides?
I see.
How challenging?
So that could be to discover. We don't know how hard it's actually going to be But one thing I do know that's going to be difficult implementing that is to handle 3D motion sickness. Because one of the reasons that we use teleportation movement instead of you walking around the space is because we know that first timer, when they go into a VR experience, the biggest problem is they're going to have 3D motion sickness. So rolling around the space, going around, like floating around, I would imagine people would get heavy 3D motion sickness. But yeah, that's a fun idea. I'll definitely get it, dive into that and see what's up. Please?
You had, on one of the slides you mentioned repeated debugging in the VR system. And
yes.
So can you just explain the challenges of debugging with this kind of system, how you overcame them?
Okay. So one of the biggest challenge and one of the most happened problem is button overlapping. So we have 4 buttons on our controller, Y, X, A, and B. So one thing that happened a lot is, let's say at the very end, at the discovery book, when we want to flip pages, we press A to flip pages. But let's say we have the pause menu and then we have pressing A to resume the game. But if we press A to resume the game, it also overlaps back into the discovery book. So you will actually end up in the second page instead of being at the front page. And then we will have to like set up a lot of different objects and then turn off this object while the other object is active. We just have to like we just have to do it over and over until one another doesn't impact one another. Another challenge that took us a lot of time is the scoring system, because just saying that, oh, you just capture whatever is inside the camera sounds easy, but then how are you gonna scan, how are you gonna know what's in the image? So what we did was we used a hitbox that is the size of the camera, and then it extends entirely into the asteroid. So whenever you hit the trigger button, whatever is in the hitbox will get captured and then get scored.
So you're basically using it kind of this geometry thing, not necessarily an image processing thing.
Yes.
Yeah, I would also like to piggyback off of that because you mentioned our debugging process. Just to kind of let everyone know, this is all of our first time like dabbling with virtual reality game development. We're usually used to kind of just 2D static game development, so it was very interesting for us to kind of unlock that testing process. Throughout our testing process and debugging, we kind of did a lot of headset testing, so very much back and forth with each other, which was definitely a challenge for us to kind of manage, specifically like with each other's times and schedules. But we did get really good advice from our one of the game developers at for Call of Duty, but when we did that presentation for her, she mentioned that we should have like a criteria for the game that we should always validify when we are testing. So that's kind of what we went through with that process, and yeah, it was very rewarding to kind of come up with this. This is our first time, so.
Cool. We will have to cut it there. Thank you.
Thank you.
Get our next group rolling.
Is it still, no, you turned it off? Or
oh, yeah. Yeah, I turned it. Push it up.
Testing. Sorry, I'm trying to figure out the feedback before I continue.
Yeah, because I was like, there's a lot of like weird noises. Because I wonder if it's like different microphones interfering with each other. So I turned it off on the last one.
I'm going to reduce the volume a little bit. People can still hear. People can still hear. Okay, awesome. Please speak directly into the microphone. If there's further feedback, I might have to go up here and reduce the volume on the microphone. Okay. And please do speak into it because that's how people on Zoom can hear.
Keep it close. Not all the way, but keep it close.
Yeah, if you can't hear yourself over the speakers, you probably need to speak a little bit closer.
Hello.
Awesome. Great.
Hello?
It's not showing up. Oh, are you? Is the? Okay. All right. So, projector should be on. Projector is on. Are you in? You are in the Zoom.
How many PhDs does it take to do AV? The answer is always
Well,
more
the
than one.
projector should never turn off. Is
That's
one
true.
thing.
I think last team had trouble with the USB-C. They were using the.
They disconnected it. Okay. All right.
Yeah, close the USB-C. There we go.
That's good. Let's see here. Sorry. I don't see a way to reduce the volume. Okay.
We good? All right, so hi everyone, thank you all for coming. We're NASA team CS 2617, and I'm sure you guys walked around the first floor, second floor. You saw most of the CS capstone projects, and they're mostly technical, right? But ours is a very unique one. It kind of sits at the intersection of art and software engineering. NASA approached us with a challenge to bridge the Psyche mission and its art program. So over these next couple of minutes, we'll kind of walk you through the process of how we approach the challenge and what our development process looked like. So my name is Jacob. I worked on testing as well as project management.
I'm Anastasia. I worked on level design and leadership.
I'm Daniel, and I worked on UI and UX design.
I'm Rehan, and I worked on deployment and documentation.
Our faculty advisor was Professor Susan Reeder from the Computer Science Department here at Seattle U, and our sponsor liaison was Cassie Bowman from the NASA ASU organization.
So I'm going to start us off. I'm going to give you some background specific to the Psyche-inspired program, talk about the setting and use case of what we built, and some of the challenges and opportunities that we faced along the way. That image that you see right there is one of the artworks from the collection. So the Psyche-inspired program invites college students from across America to create artworks in pretty much whatever form they can imagine. So that includes makeup tutorials, erased 2D, and sculptures. It's a really diverse collection. And they have a web gallery, so you can look at all of this, and they do limited museum loans. So this is actually part of NASA's broader strategy to engage the public and, as they say, spark interest and provide connections to all kinds of people. So the strategy specific to the Psyche mission really centered on participation and promotion. The Psyche capstone that we're all a part of is part of the strategy that they had to submit to secure funding for the mission. And at these in-person events, people are able to pick up prints. This is actually one of the pieces from the collection. However, not everyone is within reach of one of these events. And so our goal over this presentation is to show you how our work evolved, and we brought the collection from the 2D plane into a world that feels alive, that you can walk through, that you can experience, and that is richly layered. And it all begins, of course, with the artworks.
Yeah, thank you for that intro, Annie. So how do we actually get these artworks? Where do they come from? How do we get them into Unity and so on? So we're gonna look at our artwork acquisition process, our scanning process, some of the challenges we faced, obviously the solutions, and then finally our tech stack. So as I said, this all starts with artwork acquisition and digitalization. The image you see on the right is a screenshot of the website that NASA provided us, and it sort of serves as our primary database, in air quotes, for all the artworks. And then the image just left of it is an example of a plate that's a part of a collection. So once we got that website, we sort of came up with a subjective selection process where we picked out 15 artworks that we had shipped from Phoenix straight to Seattle, where we could unpack them, scan them in the MBC spaces, and then import them into Unity. So what does that process look like? We start on the left with the physical artwork. Obviously, we have to unpack the shipment. We had to reassemble a couple because they were broken down due to the size. And then we go through the 3D scanning phase. I'll talk about that later. But once that phase has been completed, we export those into Blender to fix the meshes, because sometimes they tend to come a little funky when you do manual 3D scanning. And then finally, we import those into Unity. Now, what are some of the challenges we faced? Well, remember the purple block? The 3D scanner is very hard to use. You have to be very still as you're walking around the object, and it takes a lot of time. Our initial plan was to go through 10 to 15 artworks per session, but in reality, we went through 2 or 3. So we knew that wasn't going to scale, and while we were looking for a solution, we stumbled upon PolyCam. PolyCam is an app on your phone that does the exact same thing a manual 3D scanner would, just a lot faster. A scan takes about 10 to 15 minutes, and the output is exactly the same. But we still had the shipping problem. Shipping takes time and it takes money. So that's when we adopted Mesh AI. Mesh AI allows us to upload 2D images and then obtain 3D scans out of the software. So the image you see on the left, the doll, that's an example of a scan used with PolyCam. The one just right of it is a part of a satellite that we scan using the 3D scanner. This is sort of what the process looks like. You walk around the object. And then finally, the scan that turned out the best was the Psyche robot that was done with Mesh AI. Now a quick look at our tech stack. As I said, we use PolyCam and Mesh AI for all the 3D scanning. We use Blender for post-processing as well as making custom shapes that would fit our needs within the project. On the scripting side, we used C# and JSON. They're both native to Unity, so we use those for scripts, data management, and any configurations we had. And then finally, Unity was our main development platform, and we built the experience for the MetaQuest 3 due to its GPU power. We also use assets from the Unity Asset Store as well as CG Trader to just make our world prettier. Now I'm going to hand it over to Danny, who's going to talk about the whole process of how the gallery was developed.
So when we first started this project, our team had little to no experience in game development and Unity, let alone virtual reality. So as you can imagine, there was quite a steep learning curve when it came to learning all of these new tools. The first several weeks of development were primarily spent trying to learn how to embed these virtual reality technologies into our Unity environment, along with playing around with these early version prototypes to test out our artwork pipeline. This learning phase eventually led us to our first playable version. This first playable version bridged the gap between that learning phase and having a real environment that you could explore. This was the team's first look at real progress. These pictures that you see here are from our modular lab scene, which is the only scene that has survived development and is now in our final product today. But there was something missing. The environment lacked cohesion, it lacked user direction. There wasn't a real incentive for users to actually explore, which leads us to our giving users direction. How do we do this? This project was designed to be shown at outreach booths for the Psyche mission, which meant that need to be quickly restarted for new users to use directly after, right? Next person in line. Second, this had to be intuitive for users of all experience levels. So first time you're using a headset, you should be able to experience our gallery as well. So we added a controls tutorial so that new users can be oriented on how to move around and how to interact with artworks, which leads us to our next feature, our artwork counter. When you go up, you can interact with an artwork, the counter goes up. This just gives users an incentive to explore each and every artwork. Last thing that we kind of needed to think about was leading players through environmental cues, like this sign, or maybe a giant artwork that attracts the attention of the user, leading them down a certain path. Thinking about all these design principles, and along with all the hard work, eventually led us to our minimum viable product. By the end of winter quarter, we pretty much had a complete experience full of 3 different scenes, full of different artworks from all sorts of different mediums. The fact that we had something so complete so quick allowed us to really refine the whole experience and take that extra time to make something that we're super proud of today. With that, I'll hand it back over to Jacob to talk about our testing process.
All right, so what does testing look like for us? We knew since the start that things like white box, black box, or even unit testing were sort of out of scope, so we mostly focused on play testing. And if I can direct your attention to that diagram on the bottom, the way this looked like was we would start a play session with someone who had no prior knowledge of the game. We wouldn't give them any tips, any pointers, nothing, and we would just watch them play. Now, as they were playing the game and as these bugs surfaced, we would categorize them into 2 categories. functional or critical bugs on one hand, and UI and non-critical bugs on the other hand. To give you some context, a functional bug, for example, would be if a player got stuck in the ground, couldn't move forwards or backwards. That obviously impacts the playability of the game, meaning that it requires our attention right away, and it probably gets a very high severity score. Whereas a UI bug would be something like an object floating in space. It doesn't affect the playability of the game, but it does require our attention at some point. Now, once those were categorized and they had a severity score, we would go into Unity and fix them one by one, again, based on the severity score. This gave us some real-time feedback on the playability and design, and our fixes were informed by actual gameplay. We weren't guessing what might be broken.
So here's just a quick sneak peek of our final product now. If you're interested in experiencing it for yourself, come swing by our booth. We'd love to give you a headset, let you try it out.
Technical difficulties.
You just really want us to try it out.
Yeah.
This is our extra.
I think we're gonna have to skip the demo, unfortunately. So let me play the video.
Jacob, do you want to save it? Right click and save as video, and maybe.
Okay, we'll play it at the end.
Hello everyone, I will be explaining the documentation, handoff, and deployment process. So for the documentation, the documentations are designed as tutorials that covers APK builds, interactions, and other topics. They're designed as a step-by-step guide to guide the team from NASA on how to manage the projects and making sure they follow along easily. They're written with they're actually designed for project core requirements, so that way we can just guide the team, make the team understand how the project works, and to have like extensibility in mind for future developments. And we want to make the project accessible enough for non-technical contributors, so that way they can pick up and learn from it. And next slide. So for the handouts, we ship the working builds, and we ship the working builds to the sponsor, so that way the sponsor can try it out in the development stages. It's good, so that way we can just get some feedback from the sponsor, the team, and the students from the events. So that we can get the idea of what went well and what needs to be improved on. So the final handout package, which is the APK file, and we send it to Google Drive because the file size is actually big, and the rest of them are sent to GitHub, so that way the team can just access them for future use. Next slide. And here's our deployment process goes. So the APK file is compatible with the MetaQuest 3 headsets because keep in mind the Alright, so the APK file is only compatible with MetaQuest 3 headset because keep in mind that the game is not available in MetaQuest store, and it takes some time to load, but we don't have time to do that, so we have to upload the APK file locally to the Google Drive headset. To install the APK file, we had to connect the fast wired USB connection between the PC and the headset. And before installing the APK file, we had to we
only have 2 minutes left, so should we continue?
Yeah, we had to just enable the development mode only once, and yeah, we'll just move on to the next slide.
Okay, so that is how we got to the tickets that you have. We delivered one cohesive space that has 3 gallery spaces, and that image that you saw of the in-person events earlier, they were actually demoing our product, and we are so proud of that. What did they report back? They said that they had strong engagement from people and that it left a lasting impression, and so we're so glad that we delivered something so great for the NASA team.
So I'll be brief. Just to wrap this up, we bridged the gap between the missions art program and software engineering. This was designed to boost engagement at live events. We support all formats of artwork, so 2D, 3D, audio, video. That was very important to us. We didn't want the artists to have to compromise in order to be included in our game. And then finally, as Rayhan talked about, it's built for extensibility, meaning that the new artworks can be added as the mission goes towards 2029. And I'm sorry, but we're running low on time. There's a couple of people we want to acknowledge. Unfortunately, I don't think I can go through them one by one, but we're very grateful and appreciative of your support. So thank you.
And we are technically at the end of the session, but we had a little bit of a 5-minute intro, so let's have some questions, and if you have to shuffle out, feel free to.
Go ahead.
Do you have any idea overall what the goal of the Psyche mission is to explore Psyche? What kind of sensors are they going to take?
Yeah, so they have a magnetometer, they have a spectrometer. So their goal is to basically get high quality imaging from the asteroid. And in fact, they have the fastest data connection that they've ever sent to space. So we're getting a lot of high resolution data back. So yeah, imaging, magnetometers, spectrometers. I think they're measuring like gamma rays. And the goal is to learn how planets are formed.
So you mentioned that you can add new artwork to this, and you sound like in this project you kind of initially struggled and figured out good ways of doing that. Are you to a point where like someone non-technical could add artwork to this, or is there still kind of a technical, like we're using the scanners and the techniques?
Yeah, I mean, I think we like to think that a non-technical person could add something. There's still open space on certain walls and objects in the game that could potentially, you know, we could put an artwork up there. I think our documentation is very detailed, very simple. So yeah, I do believe that a non-technical person could pick this up if they, you know, put in the time and the effort.
Right. There's two aspects. One is actually scanning the image and they're getting that in the program, so that part, and then there's also a part of integrating into the game.
They could do both. The scanning part is the easiest part. Go ahead.
First time user wanting to do scanning, should I go Meshy AI first, or should I do Poly?
You should try Polycam first, but Annie can speak more than that.
Yeah, it depends on your goals. If you have, like, yeah, so what was your goal? Ease of use, then Polycam. And if you have physical access to it, and you want high resolution scans, then yes, Polycam.
And I believe the subscription's cheaper.
Oh, that was the other thing. Free would be nice.
Good luck.
Meshy AI. No? Okay. That's okay.
Well, thank you everyone for listening. I think that's it. Right?
Yeah. Good job. Over again, so hopefully this makes presentations a bit smoother.
All right, well, welcome everyone. Good afternoon. My name is Max Tran, and on behalf of myself and all of my capstone colleagues, we're very excited to welcome you into this session. All three of the teams presenting today are sponsored by the Psyche capstone program, and even though they are sponsored by the same program, there's been a lot of different ways they've been able to take the goal of the program, as we'll see today. Our agenda today is fourfold. We do have our 3 capstone presentations, and right now we have our brief introduction. As we get some things started, I have some few questions that I could use your help with. So, if you could raise your hand, if you know anything at all about Psyche, have heard about the mission, heard about the goals. I know our Psyche teams do. We have some people from previous sessions. Okay, so as I said last session, Psyche has the Psyche mission, NASA's Psyche mission. It has a destination and it has a way of getting there. So could one of our Psyche enthusiasts get us started with one of those? Where are we going and how are we getting there? Okay, Shamitha.
Okay, so we're going to the asteroid Psyche and we're getting there through a spaceship.
That's it. We're going to an asteroid and we're getting there through a spacecraft. Actually, maybe, but the interesting thing is, even though we're heading towards space, the story behind Psyche actually starts here on Earth, and not just here on Earth, but 3,950 miles below Earth's surface. So this is the Earth, a picture of the Earth. And if we go ahead, let's see. Okay, so it actually starts 3,950 miles below the Earth's surface in the Earth's core down there. And the interesting thing is, despite how important the Earth's core is to so much of is important to life on Earth. Without it, we wouldn't be able to live on the surface of the planet. We don't know a whole lot about it, and we haven't been able to really take a good look at it. In fact, if you decided you wanted to go to the Earth's core tomorrow and got your big excavator and started digging, our best machinery so far, our best attempt at digging down, hasn't gotten very far. We've only gotten about 7.6 miles out of the 3,950 miles all the way down. And that was back when we had the Soviet Union. They were the ones doing the drilling tests. So we haven't gotten very far. And really the goal of Psyche, as the principal investigator for the mission says, is the Psyche mission, the goal of the Psyche mission is to explore inner space by going to outer space. And so, really, the goal of the Psyche mission is to take a look at the asteroid Psyche, 16 Psyche. From Earth, our best observations tell us that this asteroid is mainly made out of, it seems to be made out of metal. And our hope is that by heading to Psyche, by observing the asteroid, by taking pictures, by looking at its composition, we can start to get a sense of what Earth's own core might be like. From our best guesses now, the asteroid Psyche is a core of a planetesimal, of a early body that formed in the early history of our solar system that might have, in a different possible world, been sort of the seed of a new planet. So where are we today? So the Psyche mission was launched in 2023, launched from Earth. We have, let's see, we just passed Mars. As of last month, Psyche flew past Mars and was able to take some crescent pictures from its angle of approach, crescents of Mars. And and Psyche is now on target to arrive at its namesake, the asteroid Psyche, by 2029. So in 3 years, 9 months, 3 years and 5 months now, Psyche is scheduled for arrival. And scheduled for arrival. And sort of in the meantime, what all of our capstone teams have been working on together is, through the Psyche capstone program, is in these 3 years and 5 months leading up to Psyche, the Psyche capstone and Psyche Inspired has been working with teams of students to build experiences, to build games, to build ways of engaging the broader community with the mission and with NASA's science objectives. And each of these teams have taken that in a direction in an effort to raise awareness about this mission.
All right, thank you, Max.
So let's get rolling with our first capstone group of this session.
All right. Our team is Team PSY-CONSTRUCT. I am Elliot.
I'm Tim.
I'm Ollie.
And I'm Marat.
And throughout this year, we've been, and for our agenda of what we're going to talk about with our project, we'll start with what it is, how it's supporting the Psyche mission, and the nature of what we built, how we made it, like what technologies we used, and how we worked together as a group, and what we learned from this project, what we'll be able to take away from it in our future work. And then a milestone timeline taking you through all of the steps that we made to build it, the iterations and different designs that we went through. And then finally, we'll have a demo showing off what the game looks like and the cool game that it is. So, what our project is it is a web-based game because NASA needed interaction to continue throughout the long travel time that the spacecraft was taking to reach the Psyche asteroid. So our game is available on NASA's website right now. Its target audience is people that are ages 10 plus, and it's designed to be fun for any age. It was designed for people that just like to enjoy web games, and by enjoying the game, they would then learn about the mission through the ways that its mechanics integrate the real facts about the mission. What we'll be handing off to NASA is the files for the game, so that they can host it on their website, of course, as well as all of the code will be available in their GitHub, and people will be able to view it there publicly.
All right. So PSY-CONSTRUCT is a 2D space game built in Unity using C#, which was inspired directly from the NASA Psyche mission itself. The game concept is pretty simple. Players are given a set of spacecraft parts in which they must assemble and create a ship in our custom ship builder. Once the ship is up to their standards, they can then launch into space, where they'll have to navigate through a field of incoming asteroids while also maintaining their ship's movement. The goal of the game is pretty simple. It's just to reach Psyche so that we can orbit around it and study the metal-rich asteroid. Next slide, please. So for our project, we used an agile methodology where all of our work was broken down into story cards and tracked as GitHub issues so that we had a clear picture of the work that was being done and work that needed to be done. Each team member worked on their own branch to implement their own features independently and would submit for review before merging with our main code base. As a team, we met bi-weekly where we would sync up on progress, flag any blockers, and plan upcoming sprint work. And to add with that, we also would have regular check-ins with our faculty advisor and sponsor to make sure that the work being done was aligned with what our project goals were. By doing so, this kept the team not only aligned, but was able for us to split the work evenly without getting in each other's way. Next slide, please. One of the biggest lessons we learned throughout this project was the importance of having a clear and consistent communication. After the first quarter, each of us had different schedules and responsibilities, so we had to be extra intentional about staying connected and sharing updates. We also learned that collaborating work early helped avoid integration issues, especially assets like our artwork. Next slide, please. For the testing side, we took a both manual and iterative approach, or after each feature was implemented, we play tested it directly in our game to ensure it was working. We also had a pretty fair, simple sign-off criteria, which was that as long as the feature worked without messing anything else that was already implemented, then it was good to go. We didn't use much automation, as we did mainly black box testing, which worked well for a project like ours, since it was mainly visual and interactive. And with that, I'll hand it off to Murat.
Thank you, Tim. So just to go over some progress and timeline for this project. Obviously, this game didn't just pop out of the ground fully completed. We had to start from scratch, and we weren't really given any hard requirements. We had 3, which were basically don't collect user data, it needs to be a web game, and it needs to be, about the Psyche mission. So we got together and we started brainstorming. What do we want this game to be? How do we want players to play it? And so an idea started to form, and we were thinking, okay, well, maybe they're piloting the spacecraft, and maybe they're kind of going on their way to Psyche. Okay, so this is where it started, and now we're thinking, okay, well, there needs to be something more. Okay, they're gonna maybe build their own spacecraft. Okay, that's an interesting idea that we really liked. But that can't just be it. There needs to be some sort of struggle. There needs to be some sort of difficulty. And we came up with the idea of having asteroids kind of flying across the screen, and the player needs to dodge them, and maybe if they get hit, maybe they need to do something to get their health back. And so an idea was born. And obviously this wasn't fully fledged, as you'll see in the demo. This idea kind of evolved over time as we continued to work on this project. So obviously next came the spacecraft building, since we can't really work on the flight if we don't have the spacecraft. First, we created the spacecraft grid, which allows the player to drag and place parts into this grid in any orientation that they want. I won't say that there's a incorrect and correct way to do it, but there is an easy way and a difficult way to build your spacecrafts. And we wanted people to have kind of the most freedom to build whatever they want. And originally, our idea was just have them connect on the sides, nothing in the middle. But you're going to see that this didn't end up being our final iteration of the spacecraft building grid. And we were getting feedback from the Cornish art students on how they wanted to make the parts. And we kind of evolve this idea into maybe some of the parts are stackable. You'll see more of that in the demo. After that, obviously, you're done building. Where do we need to go next? Launch and flight. So for flight, you need some sort of physics. We wanted the thrusters to really push the spaceship in whichever direction you wanted. We wanted players to be able to turn their spaceship with the thrusters. So we have, you activate one thruster, you start turning to the left, maybe the other one, you start turning to the right. It's not easy, but I think getting it right is rewarding. Obviously, we needed hazards, resources, and scoring. Hazards are, what we mentioned earlier, asteroids. The player really needs to be able to, do something in the spacecraft. It can't just be them going from Earth to Psyche. Resources, originally we started out with just health and fuel. But then, we got to thinking and we wanted, this isn't exactly how the Psyche mission is. There's solar panels, and we already had the idea for the part, but it wasn't doing anything, and we really didn't like that. So we later ended up adding energy, which is a resource that can be recharged by, using your solar panels. And so this kind of added an extra layer of difficulty on top of just dodging dodging asteroids. The player kind of needed to manage their own resources in a way that would still work for them, but wouldn't kind of take over the difficulty of dodging these asteroids. And obviously it's an educational game. We need to put information in there that is accurate to the mission and to NASA's goals. So a lot of the parts have their own facts. When you drag them, they might say something, did you know about this part? And then in the flight scene, there's also more information about, how far along the project is, or the mission is, and how much time is left until the spacecraft reaches Psyche. And then, really kind of later into the development cycle, we realized that the tutorials weren't good enough. We had some text, but people weren't reading it, and they were skipping it, and then they were running into issues. How do I, why can't I fire my my engines? What's going on? Okay, well, you don't have enough energy, but that's kind of on us. We didn't explain that properly. We did not expect players to really skip over the tutorial, so that was something later in the life cycle of the game that we had to flesh out and kind of really work through. And of course, final handoff. It's just a WebGL build that we kind of create the documentation for and really hand off to NASA at the end, just so maybe that if they want to expand it later, there's enough documentation in there for them to really be able to do that simply. And with that, I think we can now move on to our demo.
All right, demo time. So let me pull this up real quick. Here is our demo. Is this on? This doesn't, okay. So we're gonna go right into this real quick. Right off the bat, we're put into our little build scene right here. This is where you're gonna be building your spacecraft. And we really wanted this to be like a very iterative approach of building it, where you might build a little bit and then kind of work on something else and try to fly it, and then try to come back and maybe do some changes around that, and really just figure stuff out along the way and not really all at once. So with that, the very first time you enter this, it's kind of in like a almost tutorial mode, where you can't really place certain parts, like any of these parts you can't place until you initially place these first bits. you'll see once you place or when you pull things out, it has these little green tiles that you can place things on to show you where. And these are just the spacecraft body parts. They're kind of these connectors for everything else. They don't really do anything other than that. It's really just fleshing out the body. Then the engines, of course, they're engines. They make the spacecraft move. But what's interesting about them is they have two different types of fuel that they use. One of them is just normal fuel from this fuel tank. And just normal fuel like this, you get a certain maximum amount that you start off with, and you can increase that by adding more fuel tanks. So having 2 fuel tanks gives you twice as much as just one. Then the other type of energy that the engines use is solar panels, where they'll get solar energy. And this doesn't have a maximum that you can increase, but instead it's going to be able to get recharged by facing them towards the sun. And then finally, the kind of last special part is this satellite dish. And kind of, this might not necessarily be intuitive at first, but the satellite dish is being used to actually repair your ship. And the idea behind that is that you'd be communicating back to Earth to be able to get instructions for how to repair it. And the instructions are, of course, not like real instructions, but it's like a little, you'll see. It's a fun little game. But then we also have these 4 sensors here at the bottom. And these sensors, they don't have an actual purpose other than like that affects your ship. But what they do is when you get to the actual Psyche asteroid, the idea is that they will scan the asteroid because, of course, we're going there to be able to do some research. And so I'm going to try and quickly build a kind of nice little ship to be able to use and fly around with. I'm going to rush through this because we are running low on time. But this seems pretty good to me. My idea here is we can have these solar panels that are on the side so that if the sun is either over here or over here, it can recharge. And we have an engine that's up here, and it kind of goes in the opposite direction of these. And so they will launch in opposing directions, and you can use them to brake, perhaps. Okay, there was supposed to be a cutscene there. That was the first time that's ever done that. Oh my goodness. Anyways, we have this tutorial here. We are gonna kind of skip through it a little bit. We have explanations of the engines, the health, the energy. We're gonna fly through that. And so we can kind of fly this around here, and we can see these different icons that are over on the sides. And over here is the, we gotta dodge these asteroids, is the Psyche asteroid. That's the main goal of getting there. And you wanna kind of do that while avoiding these asteroids that are coming towards you. And if you do get hit, we're gonna try to get hit in just a second. It will damage you a little bit. And so here we're gonna run into this guy. Boom. You can see it. You can see it makes you drop a little bit of health. And we have it set to a very easy mode right now for the tutorial because we really did not want to mess things up in front of you guys. But as you can see, you really are supposed to get hit. Oh, look at that. And it's really not that big of an issue because you're able to repair your ship too. You can face it back. Oh my goodness. Talking while doing this is tricky. You can face it back towards Earth, which is behind us where we started. This is the little satellite dish down here. You can hold this down, and this is kind of the communicating back and forth where if you get that right in that little area, it will heal you. I'm not sure if you guys saw it heal.
For the sake of time, while you're continuing to demo, we should start taking some questions.
Okay, sure, yeah. Let's hear questions if someone wants to keep an eye out.
But give us the eye candy while you're answering questions, or not.
Yeah, we kind of crashed. That's okay, though. Yes, Aiden.
It looks like this game is really physics-based, and simulating physics can be really difficult in game engines. So I was just wondering if you guys could speak a little bit on what that process was like for you adding physics to your game.
Yeah, so a lot of the physics does initially come from very basic work from the game engine itself. They have a lot of the basic things to that, but we had to do a lot of additive work to that. We had to make the spacecraft fly just in like this very ideal way that makes it feel easy enough for the users, but also realistic enough to not feel like it's just a little game, I guess, even though it is a game, but you want it to still feel realistic, right? And so you had to get a good in-between. And so there was a lot of just small things, and you might have not noticed it from that, but that's really the goal. And so kind of coming up with that in-between is the important part there. Yes, Simon.
So you mentioned the Cornish College of Arts assisting with this game. What did that collaboration process look like?
Yeah, so we initially had, it was Oswald's idea here to talk with them, and we joined in with that. And we've been in communication with them for the last several months, where we would talk about, oh, these are the things that we want, and they would send us little smaller versions of it that were less quality, and then we would say, okay, yes, we like this, or oh no, we don't like this, and they would. It was a big back and forth, but they of course delivered some really great art. This is by them. Just about everything that you saw was by them, and we're really happy with how they did. Yes.
Are there any additional cool optional objectives that you can?
Yes. Thank you. What a insightful question. We have an option that I had to skip by due to lack of time, where you're able to fly and slingshot around Mars. If you might have seen a little mini map appear down here, that was kind of an assist for helping you go that way. If you follow the path that it was on, it would give you bonus points for trying to follow it, and that's coming from the actual Psyche mission, where if you are, that they did do that to try to be more efficient fuel-wise and speed-wise. And so, yeah. Yes?
What was your favorite part working on the game?
That's a great question. I think really, I'm gonna, do you guys have, I just realized I've been talking this entire time.
Yeah, I mean, something that you guys didn't get to see is that there is actually like sound fully integrated. Everything in the game has sound. There's sound for collision, but my point is that especially me personally, I really enjoyed doing the music integration. It was very fun just sitting there and listening to the music. And there's different kind of drum tracks that go in and out, and doing the timings on those was definitely very enjoyable for me.
I think my favorite part was working on the game balance, trying to figure out like how much force was the right amount of force to use for thrusters, how much time should you give users to reach the Psyche asteroid for maximum score, and managing like the fuel and energy bars, which was also influenced a bit with our testing, where we had various people try our game and tweaked those values to make it make sense for the skill level that people would enter the game with.
All right, well, I think that is our time, so thank you all again. Have our second group come on down.
You can always jump in, but you can be like default then, I guess.
Is there any side you guys want me on?
Let's see. Sorry?
Blake stood in. Do you want me to do slides or?
Sorry, give me 1 second. Yeah, sure, we can do slides.
So I could do slides.
Sure. Yeah, sounds good.
We'll stay on this side then, and then we can switch off when I speak. Does work. I mean, you're going.
Oh, yeah. Okay. Of course. I just want to make sure if the audio is working as well.
This mic is sick, but I don't know the signals. Let's test real quick.
Disable sharing. Pause. we don't have to it's gone online. Yeah. Sounds good. They got the QR code.
check audio, but it seems like a thing we could present without it.
You should be able to, like, if you see here. Where's the? Yeah, no, that's going through.
Okay.
It's just lighter.
Okay. Sounds good.
Yeah.
Nice. All right, and then how do I? Wait, can I? It's not showing up on there.
Yeah, it's probably right here. How are we connected?
Oh, and currently you're sharing your own screen, which is showing the Zoom currently. So you've got.
Oh, okay. Wait, how do we connect it through there? It's just the USB-C breaker.
Yes,
you're good. Okay, we're good.
Well, now you're on the wrong source.
But now we can
Switch.
there over here. Maybe close that tab.
This is, I didn't understand what was this messy. It's VGA to HDMI to USB-C.
Oh.
So we're supposed to be on the VGA? Okay, perfect.
All right.
There you go.
Wow. Okay, cool.
That's okay. All right.
Testing. Testing.
Testing. I'll do slides.
Take it away.
Hello, we're Return to Psyche. Our faculty advisor is Professor Nate Kramer-Herman, and our capstone sponsor was Dr. Cassie Bowman. I'm Blake Anderson. This is Ashwath Srinivasan, Ayman Hussein, and Aiden Liam. So for our central goal, it's just to get people inspired about Psyche. And what better way to do this is through video games. They're fun and engaging, and they teach you a lot about whatever content you're playing. And we kind of do this through two ways, active learning and passive learning. We have a lot of pop-ups that give you just facts about our solar system and Psyche in general. And then we also have, like, what we thought was about passive learning is just kind of getting ways that people sort of learn about things passively. And one of the ways we do this is with the location of Psyche. So playing our game, you'll pass very familiar places like the moon and Mars. And then all of a sudden you'll reach Psyche. And that kind of gets you to like realize, oh, this is located past Mars, it's in our solar system, and it kind of gets you that sense of this is actually a real place that we're going to visit.
All right, and now I'm going to give a brief overview of our overall game concept. So at the beginning of the year, the first thing that we did was we created a few guiding principles as to what we wanted our broader game to look like. And all of these decisions were designed to, above all else, serve the goal that Blake was just speaking on. So to that end, we were given two main requirements from our sponsor initially. One, the game had to be web-based, and that means that it had to be playable online on a browser with no downloads necessary. And two, it had to be compatible with mobile devices. So if the central goal of our game is to spread awareness, then the idea behind these requirements is to make the game as accessible as possible. But beyond that, we also want to make sure the game was fun. So we began inspecting a lot of really famous web-based games and mobile games, trying to find a few defining characteristics. And we came up with things such as normally online and mobile games, they tended to have one or two core gameplay loops that were highly replayable. And they also tended to have unlockable things over time to kind of instill a sense of progression. We found ourselves particularly drawn to the endless runner genre because that game genre has been successful since the 2000s. You know, you can think of like Subway Surfers and Jetpack Joyride. Those games, they're super simple, they're very lightweight, but at the same time, people can play them for hours without getting bored. And furthermore, we also thought the endless runner genre would just fit our game's theme very well, as it's supposed to be about the Psyche mission, which is a probe launching into the infinite vastness of space. So that's our core game concept. It's a arcade-style endless runner game where the player will pilot a probe past various obstacles, and along the way, they can unlock various upgrades that are supposed to help them prepare for the dangers ahead. But beyond that, we didn't just want to make a game that was fun and happened to be about the Psyche mission. We wanted players to end our game wanting to learn more. And so we came up with a few more guiding principles to further that specific end. So, like, first of all, we decided to have our game take place in the futuristic setting. To be specific, our game takes place in the year 2223, which is 200 years after the initial Psyche, real-life Psyche mission launch. So a little bit of like coolness there, we thought. And the reason for that is simple. There are a lot of really cool, more fantastical elements about space exploration that just aren't really feasible with present-day technology. So by setting our game in the future, we can include some of those more fantastical elements without misleading players as to what the present-day realities are like. In a similar vein, we also heavily monitored the amount of creative liberties that we took. Again, we didn't want to mislead anyone, but there was also a second motivation there, and that is that we really believed in the mantra of inspiration over education. As Blake was saying, there are a lot of things that are about our game that try to maintain an air of authenticity. So in between runs, fun facts will pop up on the screen. People can see constellations in the background fly by. A lot of the real-life ship upgrades, they're based on pieces of real-life machinery. The idea here is that by showing some of these more wondrous elements of space, then we're not going to have to ask players to want to learn more. They're going to want to naturally learn more on their own. So that was a few of our core guiding principles, and now I'm going to give it to Ashwath for artistic direction.
Yeah, so pretty early on, we knew that we really wanted to prioritize artistic direction in our game. With this being a computer science capstone project, it wasn't necessarily in the guidelines that we had to do so, but just from games that we've all played in the past, we know that the ones that we like the most are the ones with the strong artistic identity. And so initially we attempted to achieve this by creating and curating our own assets, but it quickly proved to not be very feasible. With curating assets, we're limited to free asset packs that we find online, which often are going to lack individuality. And then when it came to creating our own, I mean, again, as computer science students, we really had no artistic ability among the four of us, so it was not really feasible. So actually, our faculty advisor, Dr. Nate Kremer-Herman, had the idea to reach out to the Cornish College of the Arts and work with some students over there. And this was a really exciting opportunity because it meant that now our computer science project is turning into a hybrid between an art project and a technical project. And that was just really cool to work with students from a completely different discipline than we're used to. For those of you who aren't familiar with the Cornish College of the Arts, they are located in Seattle, right over in South Lake Union. They were recently acquired by Seattle University just over a year ago, and we specifically worked with the Film and Media, Animation, and Game Arts department. And our point of contact over there was John Bond, who was instrumental in putting this whole collaboration together. He is an adjunct instructor over at Cornish and also has game development experience of his own, being the director of Keywitch Games, which is also a Seattle-based gaming studio. Our early conversations in the collaborative process involved a lot of talks about our art direction. We had some ideas that we shot off to them, and then they got back to us, talking about what would make sense to do given the timeline, and also what art styles would make more sense. And because of this, we really had a lot of conversations about scope. So we had to realize what we could actually get done within the time frame, and that meant letting go of a lot of features that we were actually really excited to implement. And initially we were pretty sad about making some of these sacrifices, but we found that limiting the game to the bare essentials actually made the game a lot more fun to play. Kind of like Aiden said, like the endless runner games are really fun because of how simple they are. So by getting rid of all that bloat, we were really able to focus in and make that central gameplay loop as fun as possible. And another thing that came up a lot was managing deadlines. Because our team had now more than doubled in size with the addition of these art students, we needed to find a way to have an iterative process and also be able to get our deadlines in on time. And that meant giving the art students a lot more time to work and making sure that we set deadlines far before the actual deadlines. And through this iterative process, we were able to get from the early concept art that we were sent over by Cornish to what you're going to see in the final game today. And just as a reference, this is kind of what our game looked like before we implemented any of the Cornish assets. It looks pretty bare. You can kind of see like some of the stars in the background. And then you can see after, just a lot more polished. I think most of us here would agree that the one on the right is a game that we would want to play.
Okay, and of course, to credit the artists, all of these are the students from the College of Cornish, or Cornish's College of Arts. So a little moment just to say thank you. And we can move on to deployment. Okay, so a little more technical here, but so usually after every sprint, a sprint is basically for us a 2 weeks worth of work. And we typically have a meeting afterwards called a retrospective, where we just discuss what we've worked on, what features we'd like to implement. And after this meeting, typically I would upload this code to Arizona State University's code base. So Arizona State University is working with NASA and is more so who we're interacting with, and they have their own repository of code. So once we've uploaded our code to their repository, they can then create what I think was mentioned earlier, a WebGL build. What that means is they have this one build that they can deploy on websites. Oh.
Sorry, I did share the thing.
Okay. That they can deploy sorry, that cut me off completely. But a WebGL build allows them to upload it onto a website and makes it interactive on any website. So the general idea is once we hand off the code every 2 weeks, they're able to deploy it thanks to Sriyanesh and Omkar at ASU. And this actually makes it really easy for us in terms of final handoff because once we create a build, it's really easy to upload it and deploy it on any specific website. And NASA has its own specific portal, which allows handoff to be as simple as we give them the code and a WebGL build, and once that's done, it's immediately accessible via a link to their website. So that's the general idea. And now we can move on to a live demo, which is perfect, 5 minutes. All right. Aiden, you want to switch over?
Right here.
I'll be on this side.
It's alt tab.
Yeah, and actually, as we're switching over, one of the really cool things about making a mobile game is that since a lot of us here have iPhones, we can, or Androids and stuff, we can actually show a QR code on the screen, and then you guys can actually scan it right now in the audience if you want. And then just as we're going through it, you can play along with us.
Oh, do you want me to keep it up while it?
Oh yeah, you just like click on that one right over there.
Okay.
And then you press that one up there. Yeah, there.
Cool. Okay, so yeah, this is how our game starts off. We have this intro scroll that kind of just gives you some exposition on the story of the game. Summary, it's in the year 2223 in the future, and the idea is that we have to go back to Psyche to mine it for...
Sorry, you can keep going. Sorry, yeah. Share the whole screen.
Or should I wait? Or?
Here. There. All right, sorry about that, guys.
Cool, yeah, so this is just like a summary. Yeah, the idea is that we're going back to Psyche to mine it for resources to build deep space spacecrafts. And then if we click the skip button up there, we get to our start screen. Main components here, we have our checkpoint system in the center, so you can kind of tap through. You can see all of these are currently locked. That's because we haven't reached them yet in the game. Once you do, they'll unlock and they can be purchasable through the coin system that we have set up. So yeah, if we go back to Earth, we can click launch, and that's going to start our run. We can see we have some power-ups popping up in the middle there, as well as asteroids falling down from the top. So the idea is you want to avoid these asteroids while also collecting the coins and the power-ups. The power-ups do different things. That one, for example, will eventually lead to a gold rush kind of thing, where a bunch of coins will pop up on screen. We have a hyperspace power-up that will increase your score, and then other power-ups that are similar. And if you keep going here, we'll see when we get to a score of 300, we'll reach our first checkpoint. And yeah, so our first checkpoint here is the moon. Once you get there, a little pop-up comes up telling you that a new asteroid's been unlocked. And now this is an asteroid that's going to start falling from the top as well, teleporting asteroid. Let's see if we can get one of those. So as the game progresses, the percentage of which asteroid spawns changes. So harder asteroids will spawn as you play more and more. Yeah. And then yeah, if you take a little bit more damage here, we can see your health bar on the left here kind of goes down. And then now the mission has been terminated since you lost all your health. And then I'm going to hand it off to Ayman really quickly to go over the mission report slide.
Okay, so the mission report slide, our mission actually terminated early because we didn't reach Psyche. So at the very top, we have the distance traveled. We tried our best to make the number as accurate as possible. basically between the different checkpoints like Earth and the Moon. We know that as a real life distance. And there's math that you could do to make it a relatively accurate calculation of how far you've traveled. You have your final score. You have the coins collected as well as how many asteroids you've dodged. And if you want to pop into the shop real quick. Okay, so you probably noticed that the asteroids fall fast and we don't move very fast. So how we get around that is speed. We have upgrades like speed, health, more health points, you can survive longer. We also have armor. And then moving on, we also have components. So these components, you're only able actually to equip 2 of them at a time, but they are modifiers to your ship. And then power-ups, you can upgrade the duration. By default, they last 5 seconds. Like the gold rush could last 10 seconds. You get way more coins that way. And that's the general idea. If you want to pop over to the settings. So settings, we have background music that unfortunately you can't hear right now, but it's really nice and cool. Sound, left-handed mode that toggles which side all the, oh it's loud, where all the UI is. And then colorblind mode, I tried to support all the 3 primary forms of colorblind mode. It adjusts the color of the outline because typically it's red, but people have different vision capabilities. And then finally we have our stats screen as well, which covers all the stuff you typically expect, like high score, how far you've traveled. And these are in AU units as well, to be a bit more accurate. But that's the general idea. I think we're over time, so let's get to questions.
Time for a couple questions, preferably while the next team's getting ready.
Are you able to change the color of the asteroids?
The outline specifically. So if you wanted to pop over to settings, the idea is you shift it to a color that a person with that specific colorblind or that color deficiency is able to see. For like red and green colorblindness, you would multiply the value of it by a certain. There's a set amount of values, and it shifts it so that they can differentiate between red and green. So the outline for the asteroids would change. If you have protanopia, then it shifts to like a light purple color for people who don't have that deficiency, but it'll be able to be differentiated. So that's the general idea. Yeah. Any other questions? Yes. So that's the beauty of it being a web-based game. You guys were able to access it via a QR code. So we did primarily black box testing. Unit testing is kind of, you could do that for the scripts, but primarily it's just testing how the game flows. We initially wanted to hand the game off to our target audience of like middle schoolers, but it's hard to coordinate that. So it's been mostly like my younger cousins and their younger cousins just testing it out and then saying that button's too big or I don't know what this means. So that's primarily how our testing has worked. Okay, any other questions?
Okay. All right, thank you. Let's round out the session with our next group.
Testing.
Test.
Hello, everyone. Thank you for joining us today. We're one of the NASA Psyche web-based space games. I'm Shamitha. This is Remy, Abby, and Mohammed, and our game is called COREBOUND. Our sponsor is the NASA Psyche space mission. Our sponsor liaison is Dr. Cassie Bowman, and our advisor is Professor Kevin Lundeen. And with that, we'll get started.
Sure. So, main idea, the scope of our project, we were continuing work on the NASA Psyche mission. Like the other games you've seen, we were given the task of creating something that inspired people to learn more about the mission. The way we did this was by building a 2D web-based game inspired by the popular game Among Us.
what we did was we set our game 100 years in the future. It's on a return mission to the Psyche asteroid. During this mission, the Psyche 2 is returning to the Psyche asteroid with a lonely robot on board the ship, with players tasked with controlling the robot, completing mini games, and exploring different parts of the ship. We have Psyche fact cards that are associated with each minigame so that players can learn about the Psyche mission along the way. As for our development, we used an agile and Scrum-based development workflow. Basically, along the way, we had weekly meetings at the start to get our project, get associated with our project and plan out the design of our game. Then eventually, once we became a little more familiar with the Scrum development workflow, we moved into bi-weekly meetings with meetings to go over progress on our game, blockers, and goals for each of our sprints. Finally, we incorporated sponsored demos and feedback sessions to understand ways that we should improve our game, and then we collaborated across all facets of development across the entire year to eventually refine our game into something that's deployed on the Psyche website.
So now kind of moving into a summary of a quarter-by-quarter breakdown of kind of our process with the game. So starting off with fall quarter, this was kind of the quarter where a lot of us were both introduced to the game, the mission, and also each other. So we spent a lot of time kind of trying to figure out the overall game concept that we wanted to go with as a team. You know, compared to a lot of the other capstone groups, we didn't have as much requirements or a specified structure that we had to follow, as there was a lot of creative freedom. So this took us a little bit of time. Once we figured it out, we kind of moved into defining our MVPs, requirements, and our project scope. So kind of trying to figure out, you know, what do we want out of the game when it's all said and done, along with some of the things that are going to be included in the game and left out of the game as well. Building on top of that, we started to create wireframes, storyboards, and a systems diagram. So kind of just trying to figure out the actual structure of the game, especially as we started to move into implementation in the following quarter. Just having those references was a very big help for us. And lastly, for fall quarter, we spent time kind of trying to figure out the technical direction that we wanted to take. So I'm kind of figuring out how we're going to be actually developing, figuring out how we're going to be pushing implementation, and also testing as well. So we ended up using Unity for our implementation and also our testing as well. And for pushing our changes and implementation, we used GitHub. So fall quarter being a time for planning, winter quarter was a time for actual implementation. So one of the first things we did at the start of winter quarter was kind of implementing the game using Unity. So for a lot of us here, this was our first time doing game development at all. So we spent a lot of time just trying to figure out how to actually use Unity itself before just hopping into things. But once we kind of figured out how the actual layout of Unity worked, we started off by building our main hall as our central hub. So this was our first chance to actually you know, learn how to do things such as importing assets and just learning how to use Unity as a whole. And this is something that kind of prepared us for what we did next, being creating our ship layout and our room navigation. So this was a pretty big feature within our game as well, as we were all responsible for creating a room within the ship. So we spent a lot of time just trying to figure out, you know, what rooms would be viable for the game, and also just talking within ourselves to figure out, you know, what did we want to include as a potential room and what we didn't. Once we kind of figured that out, we added another feature being our minigame triggers and our Psyche fact cards as well. So this is another big feature within our game, just having mini games. As you know, in each room was given a mini game, and we spent a lot of time just trying to figure out how to actually implement the mini games within Unity, along with figuring out, you know, what are some of the games that may work, may not work, and yeah. In regards to our Psyche fact cards, this was more of the educational factor that we wanted to add within our game. As you can see, we had the mini games for fun, and we also wanted to make it engaging for the user so that they actually learn from playing our game. So at the end of each mini game, there was a fact card that was also released at the end as well. And lastly, we spent a lot of time starting with our time-sensitive mini games as well. We felt it could be a little bit repetitive for users to kind of go around in circles and play the same games within the same rooms over and over. So we wanted to add something just to keep the users more feeling more interactive with our game. And yeah.
So for spring quarter, we had a few main focuses. One was finishing up the logic behind gameplay progression, doing final polishing, testing, and handing our game over to our sponsor. So we added another time-sensitive minigame to the ship, as well as an additional level for each of our room's minigames. And doing so just added some more variety for the player as they go throughout the ship. We also added sound effects and background music to provide more substance to the game. And we finished up any bugs that we ran into during testing. And testing was a really big focus for us this quarter with both playtesting and unit testing. Playtesting, if you don't know, is the process of having other people play the game and getting their feedback. This is really important because we've been playing this game for the last 6 months, so it's kind of become second nature to us. So getting new people in and getting their feedback was really important to learn what stuff isn't intuitive to players. We also had to do unit testing, which is the process of testing the smallest functional part of your application in isolation from the rest of the code. And this was important because it was one of the few hard requirements that was given to us by our sponsor, where we had to get at least 75% of our code tested. So getting that number up was really important. And lastly, we focused on handing our game over to our sponsor. We talked a lot with the master students over at ASU to get our game up on the website. And you can see right here, it's up on the Psyche Capstone Web-Based Projects website. And now we can get into the demo. So this is our start menu. As you press start game, a cutscene will play that introduces you to the game storyline that Remy mentioned earlier, so that the player kind of knows what they're doing as they get into the game. You'll start in the main hall of our game. This is the little robot guy that you control. You'll have an arrow that points you to which rooms you need to go into. This room down here at the bottom is the cargo room, which is the room that I was in charge of. Basically, space turbulence has caused the boxes in the room to go out of place, and it's your job to push them back into their designated targets, which you can see with the red markers. And doing so, you will get a fact card about Psyche, as well as your score will increase. And you can see your score with the progress bar to the left. And this room to the left here is the lab room, which Shamitha was in charge of. You'll walk in and interact with this box at the bottom, and it'll tell you that there's something a little bit off about the room. And if you notice in the corner, there's this weird green spill, and you will learn that there has been a chemical leak in the lab, and it's your job to clean it. So you'll collect this broom, this beautifully designed broom, and you will clean up the spills just by walking over them. And you do this while maneuvering around the different obstacles in the room. And as you do this, you will once again get a new fact about Psyche, and your score will increase. As you can see here. So this room at the top is the power room, which was made by Muhammad. Here you learn that the generator's power cells are misaligned, and it's your job to fix it. You do this by tapping spacebar when the blue line, you'll see, yeah, when the blue line is over the yellow area. And doing so will realign the power cells, and once you do that, you again get another fact about Psyche, and your score goes up. And this last room to the right here is the control room, which is created by Remy. Here you learn that the ship's trajectory has gone off course, and it's your job to fix it. You do this by pressing space or holding space for the minigame. And for this game, your accuracy changes how many stars you get for completing the game, and only if you get 3 stars will you get the fat card and your score increases the most. Lastly, this is an example of our time-sensitive minigame. Here, an asteroid hit the ship and created a crack in the hull, and it's your job to repair it. You'll have a timer that counts down, as well as a red arrow that points you to where you need to go. When you find the damage, you have to repair it. And for this minigame, you will not get a fact by completing it, but if you let the timer run out, your score will decrease. So it puts you further away from Psyche. Then lastly, you can see all of the fact cards you've collected by pressing the fact card button in the top left. This is just a demo. If you want to play the full version, you are more than welcome to. It's on the Psyche website.
Thank you, Abby, for the demo. So we had a lot of valuable takeaways from this project, and here are the main ones. So firstly, we got to develop a game. So prior to starting Capstone, almost all of us had never made a game before, and all of us were new to our game engine Unity. So in the beginning, there was a bit of a learning curve. A lot of it was figuring things out as we went along, especially like towards the beginning of the winter quarter. Additionally, we also gained experience using, with our version control, using Git and GitHub, and also with the Agile methodology for our project management approach. But beyond the technical side, though, a large aspect was trying to find the balance between creativity and feasibility. As mentioned, like our project was, we had a lot of flexibility, and we had to constantly define and redefine what we could actually complete and what we want to prioritize and what we could have finished within our time frame and our resources too. And this ties into managing our scope. As mentioned, lots of flexibility with creativity. We had to really figure out what we could accomplish within our time frame, and we had to really figure out what we could achieve in these past 9 months. And overall, we learned how to work together. We navigated through many roadblocks, but today we have a game for you to play. So as we showed you, this is our game. It's on the NASA web game portal. If you scan that QR code over there, it'll take you to our link tree where you can access the web portal. I recommend playing on your computer for the best experience. Our link tree also has our LinkedIn. So if any of you want to hire us, please connect. Please check that out. We'd love to connect. But yeah, that's all for us. Please let us know if you have any questions.
Yeah, go ahead.
I'm interested in the interpersonal dynamics. How did you resolve conflict if, half the group wanted to do one thing and half the group wanted to do something else?
I think it was a lot of compromise of not like getting rid of anyone's ideas and more so finding a place where we can include one person's ideas and the other person's ideas. We wanted to make sure that everyone's voices were heard and everyone's ideas were implemented, given, if we had time. So it was really important for us to compromise on that.
What was it like making 4 mini-games versus just one big group?
Yeah, I think by splitting it up and having different mini games associated with different rooms, it made the development process a lot easier because we were able to allocate one person to work on one mini game while another person worked on another. So it did resolve some merge conflicts. We weren't having to fight with each other on code changes, so I would say it helped a lot.
Yeah, so at the beginning, while we were still in our planning stages, we talked a lot about what rooms we wanted to do. And as we designated who was doing what room, we also described what mini games we were doing. So we kind of came to a consensus on that before we, went and individually developed each mini game.
I'd say it was definitely a long process. That first quarter was all design, no code. A lot of us were ready to sort of get into it, but I think that spending that first quarter on only design, fleshing out what we wanted to do, saved us a lot of stress later.
Take one more question.
I definitely would. One thing that we were talking about was some sort of Easter eggs in there. Another thing, we wanted to do some trivia associated. Right now, obviously there are fact cards, but there's no real reason to sort of look at them. So if we could associate some sort of Psyche trivia or something like that in it, it would be good. We're also thinking about adding some sort of power-ups or things like that so that you were able to move around the ship faster, or different creative things like that.
All right, let's thank our speakers again. That concludes our session.
Let's walk away because I think the audience is
Thank you.